Okay.
Perfect. Okay, so I can see that we have people joining in. Thanks everyone for joining us today. Welcome to the workshop with Luis Serrano. We'll be starting shortly, but before that, I would just like to give everyone some guidelines for the workshop to make sure that it's also smooth and engaging. Couple of guidelines, just please make sure that you are on mute unless you're asking a question to avoid any kind of background noise when Luis is speaking and teaching. If you'd like to speak, you can just use the raise hand option and wait for Luis to call on you before unmuting. You can also drop your questions in chat anytime. And since this is an interactive discussion, we just want to make sure we encourage everyone to participate. So please be respectful, give others a chance as well. And if possible, keep your cameras on to make sure the workshop is more engaging. Moreover, don't worry about the recording and the resources. We'll be sharing them with you afterwards, most likely early next week. Finally, that's all. We're very excited for the session, and Luis, you can take over. Thank you.
Thank you, Navi. Thank you, everybody. I'm so happy to be here. Welcome. I hope you've been enjoying the conference. And yeah, so today we're gonna talk about a visual journey through transformer models. So as Navi has said, yeah, I like this more. I like to have a more of a chat than a monologue. So definitely, I'd love to hear your opinion. Sometimes I will ask questions, in which case you can answer either by typing or by or by just talking. And if you want to turn on your camera, you don't have to, but that's a bonus. Then that'll actually fun for me. So hi. Cool. All right. So let me tell you what we're gonna do today. It's gonna be 3 hours with a break around half of the time. And we're gonna do 4 things. So we're gonna talk about transformers, like their strengths and weaknesses. We're gonna talk about their architecture, actually in great detail, but I don't like formula, so you'll get a very visual, very visual approach to how transformers operate. And then after we learn how they work, we really learn how to get the best of them. So things like retrieval-augmented generation, things like agents, things like all these things. More focused on, why we need them. What exactly is it that agents are going for? And what are the strengths and weaknesses that we're trying to either mitigate or get or use to our favor? And then we have a couple of labs on agents that we'll get to at the end. Okay. So as I said, any questions, any comments, everything, by all means, I'm all ears. So let's start with strengths and weaknesses of LLMs. So you may have seen you may have, I'm pretty sure you've used them extensively. So and anyone want to share any strengths or weaknesses you've seen? It could be in the chat or talking. It could be something like, it does this well, it doesn't do this very well. And I will write a couple myself. So any thoughts? What are they hallucinating? Yes, yeah, very good. They certainly hallucinate. Things that they do well, I feel like it, yeah, biased, I mean, very good. They speak well, right? Like, but by the way, Navina, are we recording this? I don't see
Yes,
the recording button. Okay,
it's
perfect.
getting recorded.
It's being recorded. Okay, sounds good. Robert says, too eager to answer, not good at saying I don't know. Yes, exactly. That's very bad. I really think it needs to start saying I don't know. So let's start with the strengths. It speaks well. You can't never really, it knows the lingo of every subject, right? Like it's someone who's seen a lot of stuff and knows how to sound like an expert, even if it is not an expert. I can talk about many topics. It follows orders well. I trust it with orders. If I say summarize this, get me the 3 best top points on this, I trust it. I'm not going to trust it 100% for anything, but I trust it for that more than for like medical advice, right? Hallucinates, like Sayed said. Yes, Felix just said exactly. Yeah, exactly. Excellent summarization of documents. That's where you trust it. And we'll see why. We'll see why the strengths and the weaknesses. It doesn't always tell the truth, as we know, and as many cases we've seen. Cases some lawyers who took it to court with some stuff ChatGPT told them, and cases and dates and stuff, they were all completely wrong because it knows how to sound correct, but it has no notion of correctness. Srinivasan says generates SQL code well, given the context and the prompts. Very important. Yeah, given that you prompted well, it's good at code. I read a lot of code with it. I don't let it by itself, but if you guide it correctly. Weaknesses, it doesn't know. It has no concept of the truth. No concept of the truth. It's not a database, okay? It may get used to the truth. So people say it hallucinates a few times. I think it always hallucinates. Sometimes it happens to hallucinate the truth, but that's it. Here's one. Oh no, and it compensates with an excess of confidence, right? Like what Robert says, it doesn't know how to say I don't know. Big problem. Here's a weakness and a strength that I see. Srinivas says, yeah, proof of concept goes well, production seems hard. Yeah, absolutely. It has its limits, right? Here's my favorite weakness and strength, which kind of puzzled me for a while. Have you ever asked it to tell you a joke? Not a joke it knows, a joke that it comes up with by itself. I did, and it says, why did the cloud start a podcast? Because it had so many high thoughts to share. No, that's very bad. It's not good at telling jokes. So, but on the other hand, have you ever asked it for a poem? It said, write a poem of machine learning in the style of Shakespeare. Oh, wondrous art by mortal minds designed to teach cold steel to think, to learn to can. That's pretty good. Robert, yeah, this is definitely at that joke. Yeah, the poem is really good. Now, I'm not saying it's good for a poet. Like a poet may look at this and be like, it's not that good. But for me, who knows little about jokes and little about poems, this is a good poem and a bad joke. That drives me crazy. That drives me crazy. Because if you show me the poem, then I say the model can look at all the poems and generate a good one. It can mimic the data it's given. Then I look at the joke and it says, no, it looked at all the jokes and it can't generate it. It could not replicate the data it's given. So is it smart or is it dumb? Is it a good model or not? Can it replicate the data it's given or can it not? The answer is there's we'll put this in pause and I'll come back to this. But there is a particular strength and weaknesses that of language models that makes the joke the exact Achilles heel and the poem a strength of it. And we'll see. And once you know this sort of like this strength and this weakness, it just pretty much unravels how they work and what justifies agents, what justifies RAG and stuff like that. So we'll get to that through the scenic route. So I'll get to that by maybe the second part. But think about it. While I talk about language models, think about what could be that strength that makes it write good poems and that weakness that makes it tell horrendous jokes. So we'll get to that. But let's go to the basics. Let's go to what's discriminative and what's generative AI. So let me ask you a question now. Feel free to put a thumbs up, thumbs down, put in the chat, or even just talk. What do you prefer, a multiple choice question or an essay type question? And by that, I mean, what's easier, right? Exactly. Everybody says multiple choice question. It's definitely easier to do multiple choice question than to write an essay, right? Give me, and the multiple choice question is basically predictive ML. Essay type question is basically generative ML. Why is it easier? Give me a couple of reasons why multiple choice question is easier than essay type question. Choice versus generation, exactly. Yeah, good job. Robert says limited choices. Yes, you know the answers. The answer is there. I cannot look too dumb in a multiple choice question because I can just say I missed the question. But in an essay, they give me all the potential to show how much I don't know. It's a blank sheet of paper to show my non-knowledge, right? Determinate, definite, pointed and specific. Yeah, Ananya says not a variable answer. No room to be asked. Absolutely, right? Good job, everybody. So one thing is, yeah, you can guess. You cannot guess an essay type question. For example, requires understanding the language. If you barely speak a language, if you understand a language but not speak it, like if you're at the Duolingo level of like I can answer questions, but I can't really talk. You could do a multiple choice test, not with an essay. Essay, you can't fake it, right? So the main thing is this: multiple choice requires understanding, whereas essay type requires creating, and understanding is easy, creating is hard. I can understand how a Picasso looks like. I can be an expert and tell you what is a Picasso. Only Picasso can draw a Picasso, right? I can return a dish to the kitchen and be like, I have I have a lot of feedback on this dish, but I can't go and cook it, right? So for computers and for humans, understanding is easy, creating is hard. And as I said, understanding is predictive machine learning, is answering multiple choice questions, and the essay type question of generating is generative machine learning. So 10 years ago, when like machine learning started becoming a household name, that was because of predictive ML. Who remembers when it started it started being able to determine if an email was spam or not? That was a multiple choice question, right? It's gotta kind of understand the email. Or he remembers when like it started saying, oh, a cat is in this image, identifying, classifying images. That was huge at the time. Now it's like prehistoric, but at the time I remember like everybody was shocked when he just be like, look at a cat and be like, yes, there's a cat. Like, that's amazing. Generative ML took 10 more years because it's much harder. Now you have to write the email, or now you have to draw the cat. That's much harder than saying if something's a cat or not, right? I cannot draw a cat, but I can tell you if something's a cat. So basically, we have this premise. And I remember 10 years ago being in Silicon Valley in talk, there was always a talk about a chatbot. Everybody wanted to build a chatbot. That was the holy grail of AI. Because there's no old movie, futuristic movie without a robot that talks, or a car that talks, or a fridge that talks. Anything talks, right? You needed a chatbot. And the question that basically the scientists were scratching their heads is, we have an understander machine. We don't have a creating machine. We have a machine that understands text. It can tell you what you're talking about. How do you make it talk? That's not easy. How do you make it talk, right? So help me out. I mean, let's remove the computers out of this question. And let's say that we have a magic, a crystal ball that will answer any multiple choice question. And we take it to an exam, and oh, surprise, the exam is about, it's an essay type question. So what do we do? Help me out, give me some ideas. How do you write an essay with a crystal ball that only answers multiple choice questions? Felix says you can't. That's pretty much the answer. Oh, see, I got it. Yeah. One word at a time. Yes, Remosa says create sentence out of the options. Yeah, we could start asking it stuff, right? Like, how should I start? From these 4 starters, which one is better? But yes, see, and Alex, actually, the way to do it, yeah, Robert says make the essay into small pieces, decompose. So a lot of ways to go. And as a human, we could use it in smart ways, right? Like we could say, hey, out of these 3 openings, which one should I use? But the computer knows much less. So the computer has to do what was suggested here, 1 word at a time. So the first question, it sounds like a stupid question, but the first question is, I'd like to write an essay about the Renaissance. What would the first word be? And we give it all the options. This is a multiple choice question. It's a lot of options. By the way, do you see my mouse? Give me a thumbs up. Yeah, okay, perfect. It's a multiple choice question. It's a perfectly fine multiple choice. Yeah, there's a lot of options, but the crystal ball answers the, and I just write the. Okay, nice. Now I go to the next word, and I said, next question. I said, I'd like to write an essay about the Renaissance. The first word is the. What would the second word be? And the ball says, well, probably Renaissance. And you just write it 1 word at a time. So that's exactly how LLMs work. They talk 1 word at a time. So when I think of a transformer, it generates text, but 1 word at a time. Honestly, that drives me crazy. I have to confess. I find that ridiculous. It works, but I do think that there's a better something in the future. Maybe the next iteration of chatbots is going to think a little bit ahead and revise how we generate images. We first generate noise and then clean it up. I feel that just from, this is just my thoughts, that I think that's going to be. But right now we have a machine that talks one word at a time. Muthukumar has a great question. How do you know when to stop? Well, you give it, you see this little final thing sets final period. It's another character. So you put all the words, all the question marks, periods, and you put a hard stop. And when you reach that hard stop, it's like typing an extra word. And this is the last one. Okay. So if you want the transformer to say, you say, hello, how are you? It just completes the next word. And if you want it to write a story, it's not going to write a story. It's just going to give you the first word. It's going to say like once. That's all it says. Do you want it to continue? You have to ask for the next word. So you take the once and put it back in the input, and it goes, write a story once, and it goes, upon. And then you want, okay, you want an next. It's like you go to a restaurant and you order a meal and they give you the first grain of rice, and then you have to order the second grain of rice. And it's sort of frustrating, but luckily it's fast. So you just keep putting stuff in the input, and it generates the story. So it generates one word at a time. And this drives me crazy for two reasons. First, because it's just, I don't think it's a good way to talk. I mean, I love the fact that it works, and we have a lot of tools that we use to make it work better. But this explains why it hallucinates, right? Oh. Sorry, when my phone rings, my computer also does something. Is everybody hearing me okay? Thank you.
Yes, Luis.
Sorry about that. One moment. Okay. Thank you. So this is the reason why the thing hallucinates, right? As a matter of fact, now that we know this, it should hallucinate more. Like, but there's another reason why that drives me crazy. And it's that existed already. I introduce you to the autocomplete button in the text or WhatsApp or anything like that. You say a sentence and then it gives you the next word. It gives you three. It's like 3 ChatGPTs. And it does it well. I mean, the autocomplete is a predictive model that gives you the next word in a sentence, and it does it quite well. You know, it uses a neural network. Thumbs up, thumbs down. Do you know neural networks? Have you seen them? We're gonna see them later today, in a visual way. But would love to know how you familiarize with neural networks. It's basically a neural network that you input the sentence and it tells you what they think it's the next word. Now, we had a chatbot. We had a chatbot all this time, right? Why didn't we use it as a chatbot? Have you ever tried to use the autocomplete button as a chatbot and keep pressing the middle button to make it talk? It goes, I tried this and go, hello, how are you feeling this weekend? Your kind wishes for a wonderful weekend with your kindness and happiness for your family. Love you and your kindness. It's not very eloquent. It talks like Dory, right? Like Dory, the fish. It just forgets. It doesn't have a great attention span, so it keeps changing topic. But it's not so bad because, I mean, even Dory has decent grammar, right? Because like, look at every 4 words. Hello, how are you feeling? And happiness for you, blibbity blobbity. Like it remembers a few words behind. It doesn't have a huge context window, but it's not so bad, right? But the question is, how did we get from the autocomplete to language models? Okay, so a lot of things happened, but from 10 years ago from now to now, three things happened. One is that we just have more computers. We can fit a trillion. ChatGPT has 1 trillion parameters. We can handle and compute much faster. But that's not the main reason. We also have more data, right? Like everything we say, everything we do, everything just generates data. We have a ton of data. But that's also not what did it. What did it is the attention mechanism. Okay, the attention mechanism is what made these things talk well. Basically it went from like this thing that sounds like Dory to like this thing where you can ask him about Nietzsche's philosophy applied to AI and it just tells you a wonderful thing. So what is special about it? When you create the word, they both talk one word at a time, but when you create the word kindness here, it pretty much uses the last 3 to 4 or 5 words. It just doesn't have the capacity to see back. If you try to get it to see the word hello, the smoke starts coming out of the computer. because it doesn't have that power. It doesn't have that context window or the capacity to manage it. On the other hand, we're going to come up with the word algorithms here. It can see everything back. It can see kilometers back. And not only that, we're going to talk a lot about the attention mechanism today, but here is something special. With a context window so large, how does it know where to look? Well, it looks at what's similar to the stuff it's saying right now. So algorithms, AI systems, decision-making, artificial intelligence, it looks more at the stuff that is more similar to what it's saying right now. So the WhatsApp autocomplete has a bias on recency. It pays more attention to the stuff you just said. On the other hand, this one has a bias on similarity. It pays more attention to the stuff that is similar to what it's saying right now. That's the change. That's why it can talk. Okay, that's the main change I made to talk. So in other words, if I say, for example, football, and I've been talking for a while, and I talk about the economy recently and pizza, but an hour ago I talked about football, then it just pays more attention to that because it has a concept of similarity. This is very important. One of the fundamental concepts in language models is when are two words similar and when are two words different. And so it can tell that football and ball are similar, but football and pizza or football and economy are not similar. So that's the attention mechanism. That's the thing that made it talk. It was introduced in this paper by a bunch of people from Google. Attention is all you need. 2017, and it took until 2022, I think, to make ChatGPT talk well. But this is when attention was introduced for large language models. And when you look at the diagram for transformers, this is ugly. I have a cleaner one, but this is the feed forward. This is the neural network that talks, the WhatsApp autocomplete. And this one over here is masked attention. We're going to go through pretty much every moving piece here today. But let me tell you basically how I look at it. I like to look at transformers in the following way. Let's say my prompt is write a story and the output's going to go here. First, you go through something called tokenization. We'll talk about it. Then embedding, very important. Then positional encoding, which gives the words order. And then you get to the meat of the transformer, which is a series of transformer blocks where you have feed forward and attention. We'll talk about those. And then finally, you get the softmax. And that gets to the next word once. So quick, this feed forward is the neural network that talks from the WhatsApp autocomplete. And this attention is what we're going to talk about that made it have bigger context windows. So basically, we're going to get to part 2 of today, which is we're going to talk a lot about the architecture of transformers. Quick break. Any quick questions? Anything that comes up before we dive into all this? Basically, we're going to see all these moving pieces. All good? Okay. So let's get to the architecture of transformers. I know I sold attention a lot, but embeddings are fundamental, absolutely fundamental in all of AI, I would say, in all of AI. Because embeddings are where the rubber meets the road. Embeddings are what makes, what turns computers, humans speak to computer speak, because we speak in words and computers speak in numbers. They have no idea what a word is. The most advanced computer has no idea what a word is. They only do numbers, and they do wonders with numbers. And we want to benefit from what the wonders they do with numbers and use it to language. So we need a good bridge. And the bridge is the embedding. It's really the translation. And it's really nothing more than taking words and sending them to numbers in a smart way. What do I mean by that? Well, I don't like numbers. I like positions. So here we have streets and avenues, and we have a bunch of words. Here we have a basketball, a castle, a bike, cherries. And each one has 2 coordinates. Cherries 6 and 4 because I go 6 to the right and 4 up, right? So I'm attaching 2 numbers to each word. That's an embedding. Now help me out. We're going to have the first quiz of the day. Where would you put an apple? At A, at B, or at C? Feel free to answer, either talk or put it in the chat, or do a hand signal Felix says C, Nermin says C, 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 C. Very good, C, as yes in Spanish, C. Very good. You all passed the quiz very well with flying colors because I would put the apple in C. Why would I put the apple? Good job. Why would I put the apple in C? Because the least I can ask of an embedding, as Ananya says, they're similar, right? The least I can ask of an embedding is that it puts the apple with the fruits. I put the fruits together. It's the least I can ask. If it's going to put it somewhere else, that's not a good embedding. It's the least I can ask. And it's almost all there is to an embedding. There's more, but basically it better put fruits together. So I'm going to put it in 5, 5. I could put it anywhere around here. One day somebody told me you should put it here because it's a circle. And then I realized, oh yeah, that's true. Shows the ambiguities of language, which we'll get to. But for now, yeah, like apple goes around the fruits because it's the least I can ask of a good embedding, right? Now I said 2 columns because I said that word goes to 2 numbers, because I can fit 2 numbers in my head as coordinates, but the computer can handle way more numbers. So why are we gonna use 2 when you can use thousands? I've seen them all the way to 4,096. I would say 1024. 1,000 is around what you can imagine of embeddings in a good language model, around 1,000. But basically, one thing I like to imagine further is, I mean, the numbers for similar words are going to be similar. These are the coordinates in a huge space, in a 10,000 dimensional space. I can't picture it, but I can think of it, right? But I like to think of it as that every single number is some property of the word. Maybe the color, maybe the size, maybe anything else. Now, when you look at an embedding, you can't really be like, oh yeah, the 5th number is definitely the size. No, you can't. The computer just knows, right? But if you think of it as some abstract properties of the word or combinations of properties, then it's clear that if I have the numbers for apple, because apple is similar to pear, then the numbers for pear should be similar at the very least in the majority, right? So they're located close to each other. I see a couple of really good questions, which I can address. Vikramjit says different embedding models would generate different embeddings. How does a generator know, interpret those embeddings? Wouldn't attention embeddings would be different if generators train using embeddings for a different model? Yes, absolutely. The embedding is very, very important. What I would do is I would train the embedding first, and then the transformer with that embedding. But if I change the embedding, everything changes. So if I take the ChatGPT model and I put the anthropic embedding, nothing works, right? And then I is getting to something which is semantic or structural similarity. Yes, we're gonna get to that. We're gonna get to all of that, by the way. So you did so well in quiz 1 that we're gonna go to quiz 2, right? And quiz 2 is basically a rapid fire. So here I have a strawberry and an orange, and here I have a cell phone and the Windows logo, okay? And you're gonna tell me if the words are top left, go in the top left or bottom right. You can say top or bottom. So each word I tell you, you say top or bottom. Again, you can say it, you can type it, or you can go like this in the screen. So cherry, where does the cherry go? Good job, top. Wow, amazing. A cherry goes on top. Where does Android? Android goes on the bottom. Good job. Where does laptop go? Bottom, right? Yeah. Nice. Where does banana go? Banana goes on top, right? Where does apple go? Top, bottom, middle, context, I don't know, missing. I have no idea. It could be a fruit or it could be the computer company, and we don't know. The embedding doesn't know. The scientists could come up with the best embedding in the world. They're still not going to know because a human wouldn't know. If I stand in front of you and I say apple, you have no idea what I'm talking about. I could be talking about anything. What do you need then from me? We have a problem. We can pretty much put it in the middle. That's the best we can sort of do. We got a problem and we need a solution. What would you ask me if I say apple to you? Exactly, Robert just said it. You need context, right? We need context. Context is what we need to add. And the embeddings are not going to be able to solve this problem because it's a problem of the language, right? Like the bottleneck is it's our fault. It's the numbers are fine. We are the ones who created a language with words that mean two different things. And nothing we can do. There are embeddings that are now a little more dynamic, but I'm going to tell you sort of the original solution to this problem, which is the attention mechanism. As I said, if I haven't emphasized it enough, the attention is what made these things talk. If ChatGPT was the DeLorean in Back to the Future, the time machine, I would say that the attention mechanism is the flux capacitor, is the one that made it travel in time. In case this reference reveals my age, I have a slightly newer one. If ChatGPT was the Iron Man suit, then the arc reactor is the attention mechanism. The one that makes the suit work is the one that does the magic. And it's here in this diagram, bleepity bloppity, formula, don't like. But this is basically the attention mechanism, how it works. But I like to see it more as like kind of words flying around. So help me out. If I give you some context, do you now know what I'm talking about? If I say, please buy an apple and an orange, now what am I talking about? The fruit, or exactly, the fruit, or the top, right? If I say Apple unveiled a new phone, then what am I talking about? Buying Tim Cook, that's a good one. Then I'm talking about tech, right? What word gave it away? What word made you think that I'm talking about an apple in the left, a fruit, and a computer in the right? It's probably not and, right? Orange does it. Good job, Robert. Good job. Yes, everybody's answering. Phone and orange. Correct. Orange did it and phone did it, right? They helped me, right? I'm gonna basically use those words to help us. So how are we gonna use it? Well, what they're gonna do, and check out, this is what happens. What happens is that if I have my orange here and my phone here and my ambiguous apple here, then the words basically pull each other, okay? So orange pulls apple in the only way it can. It just kind of draws a line and pulls it a little more, okay? Like a magnet or like a gravity, right? And if I'm talking about a phone, then the word phone pulls the apple down. A very little amount, but this gets done many times, okay? I call it word gravity. Basically, now the embedding for Apple is not going to be, 6 it's going to be like 8 or something like that, because the orange pulled it, okay? So when I talk about different words, they pull each other like magnets or like gravity. Now, here's a small problem. If I say, please buy an apple and an orange, we know as humans that orange pulls apple, but the computer doesn't really know. For the computer, buy is just as important, and is just as important, please is just as important. So apple gets pulled in all directions, right? You can't just be like, oh, I only want this one to pull. Everything pulls, and then apple gets pulled in all kind of directions, and then you have no idea where you're going, and that's a mess. Luckily, when we plot them in an embedding, what was the only thing that we expect from embedding? The first thing we asked on embedding is to put apple and orange close to each other, right? To put fruits close to, and buy is really far. So this works like magnets. If I have a magnet that's close, they pull hard, and if a magnet is really far away, they don't. Or like planets, right? So it just makes sure that orange and apple pull each other strong, and that when they're far away, they don't pull each other very much, right? So you just apply attention to all the words. And basically, these ones don't pull each other very much, but these ones pull strongly. So they just gravitate. Remember this a lot, because this will come up in the future. Words just kind of gravitate to each other. And then context starts appearing. The way planets gravitate to each other, right? The Earth and the Moon pull each other a lot, but the Earth and Jupiter, not so much. And so if I've been talking about fruits for a while, there's a galaxy here made of fruits activated. And if I say apple, when you're very likely that I say a fruit, because it got pulled by the galaxy, okay? So if you imagine embeddings as the universe, words all over the place, and context as gravity that puts this universe together, that's kind of what happens inside the brain of ChatGPT, okay? There's a small technicality, which is masked attention. which is that you really don't let the model look ahead of it, only behind. And that's so it doesn't cheat. So when these things are happening, you only look at the gravity before you. But that's just a small technicality. However, I think I didn't talk much about certain things, which is similarity, because I've been talking about words being similar as they're close by or far away from each other. But actually, similarity is more complicated than that. So let me tell you about similarity. As I said, if I say apple, you don't know what I'm talking about. But if I've been talking about fruits, then you know it's this. And if I've been talking about computer terms, then it's this one. And here's the thing. Let's say I'm talking about, this is my context. The other day I was walking and I thought about pear, then I realized I want some fruit. So I thought about getting an orange and what you want to pay attention is to words that are similar to apple. So I have a strong attention here to these ones and a weak one to others, right? So you pay more attention to more similar words. So the more similar words are, the more they're gonna pull each other. And so I need a strong concept of similarity. When two things are similar, like pear and apple, and when two things are different, like truck and apple. And distance actually won't cut it so well. So here's the thing. Let's say that I have orange and pear. I have a high similarity and a low similarity, which is Android and orange. I'm going to give you 3 ways to measure similarity. Okay. The first one is distance, which I already mentioned. Far away means not similar. Close means yes, similar. That's the worst one. The method 2 is the angle. So instead of looking at things that are far away or close by, I'm going to look at the angle they make with the point at the origin, the 0, 0, 0. Big angle means you're far away, not similar. Small angle means you're close by. Makes sense, right? And the other one is dot product. Give me a thumbs up, thumbs down if you've seen dot product in the past. Even if you haven't or not, I will I will still talk about it. Dot product is take the first coordinate and add it and multiply it, then the second coordinate and multiply it and add it. So I get a big number if the things are similar and a small number if things are different. However, so let's talk about those two, angle and dot product. And I'm going to start with dot product. Because even though we've seen dot product, I see some questions about angle. I'll address them in a minute. Even though we've seen dot product, it was never too clear to me why you take the first and multiply it and the second and multiply it and add it and I don't know. It just doesn't seem that clear to me as saying distance, right? So I call it the Tinder similarity. Feel free to use it in conversations. I'm trying to coin the term Tinder similarity. Let's say that I have 2 people and I want to see how similar they are in order to recommend it in an app. So I ask them questions. Long walks on the beach. Do you like them or not? Do you like pineapple and pizza or not? Do you think dogs are better than cats? And people answer yes or no. So they both like long walks on the beach. They both don't like pineapple and pizza. Seems like these people are similar. And one thinks dogs are better than cats and the other one the opposite. So how similar are these people? Well, I would add 1 every time they match and subtract 1 every time they don't match. And I add the 3 and I get, let's say, 1, right? I can also get the same thing by putting a -1 on the no and a 1 on the yes and multiplying them. Okay. Because 1 times 1 is 1, -1 times -1 is 1. So the product, see, the product is not really a product. It's like, are 2 things equal or not? If I have 1s and -1s, right? So that's why I think dot product works, right? Because if you start matching the answers to something and multiplying them, it's big if they're similar and could be negative if they're different. So that's why in my head, that's when I wrap around my head around dot product and then I add them, right? I know this, you've seen dot product, so this is simple, but I just want to emphasize some stuff that like sometimes it's not super clear to me and I just want to make it super clear. So dot product here is basically, another way to look at it is if I have in my embedding, all embeddings I'm going to use today are very friendly and have like 1 property here in the horizontal and 1 property in the vertical. So I have fruitness on the horizontal and technology in the vertical. And my embeddings for orange are 6 for fruitness and 1 for technology and for Android, for example, is 1 for fruitness and 8. Oh, sorry, I made the wrong number here. Oh, no, it's true. 1 for horizontal fruitness and 8 for technology, the vertical. And when I do the dot product, I just basically multiply the first number, then the second number, and I add them. And then I do the same thing here, and I add them. And so I get big number when the big numbers are in the same positions, and small number when the big numbers are not in the same position. So large dot product, large similarity, small dot product, small similarity. Okay, so that's dot product. Now let's talk about the angle. Xiang is asking a question. What about a small angle but two items far away? We'll get there, Xiang. Great question. When we say the angle, then we say that a large angle means small cosine similarity and that a small angle means large cosine similarity. I'm sorry, this one also bothers me. Why, if I have a perfectly good defined notion of distance, why would I want to use an angle? Like, can anyone help me? Like, why would you use an angle if you have distance? Kind of nerdy, be like, oh, we're at this angle. Be like, no, you and I are 5 meters away. That's better than saying we make an angle of 2 degrees with that post over there. Makes no sense, right? Help me out. Is there another place in the world where angle is used instead of distance? Like, is there any other place where naturally you would use angle and not distance? Yep, I see some great. Xiang says cursive dimensionality. Yes, it's easier to calculate an angle in many dimensions than to calculate a Euclidean Pythagorean distance. So that's one reason. Help me out. Is there any place in the world where you wouldn't think of distance? Would be crazy to think of distance and makes a lot of sense to think of angle. How about in the world? Yes, a compass, right? A compass would work. In the world, right? Like if I want to fly from in the globe, right? Hiking as well. Yeah, if you're going long distances, census in the globe. If I want to go from point A to point B in the world, I don't open a hole and go the direct route. I take the curve. The Earth is a circle. Circles have angles. In the world, everything is angle. Okay? That if we're close by, I don't use the angle because I can approximate it with flatness, pretending the world is flat, but the world ain't flat, right? So for distances between places, distance means nothing. Angle means everything. Angle times the radius of the Earth. And why do we care about angles? Because embeddings are more like the Earth than they are like the universe. So if I look, this is an exaggeration, right? They're not a sphere, but they are spherical in nature. They have mountains and hills and spikes and valleys, but they are more circular objects in the sense that it's better for me to look at it from the middle and see things far away where they point than to look at it from the outside and measure distances. And the dot product and cosine distance, as Robert points out, they capture magnitude and direction. They're actually very similar. If I have a unit circle, a circle of radius 1, they are the exact same thing. And if not, then you just to get this from this, you just multiply by the lengths and get something similar. So I'm going to see them as very similar. There's this identity here that is that the cosine of an angle is a dot product that joins them, right? And so I can see things like if they're completely opposite, they're at a 180 degree with cosine -1, and if they are at 90 degrees, they're like irrelevant to each other. So this kind of helps. And I think I don't have this. I think I'm missing a little slide here. But for example, picture this. Sometimes you're gonna have to answer Xiang's question. Sometimes you're gonna have two words pointing in the same direction that are very similar. If I have, for example, the word bad and the word atrocious, they point in the same direction, but they're far away from each other. Like two stars that are millions of light years apart, but when I see them from the Earth, they look very similar. They are similar, okay? In an embedding, it happens that words can be far away, but if they form the same angle, they're more similar. So that's why it's better to look at it from the circle perspective. Is there any question about sort of this? So we have the dot product and cosine distance. And the question is, which one does ChatGPT use? Does it use dot product or cosine? it actually doesn't use any of the two. It uses something called scale dot product. So it takes the dot product and divides it by the square root of the number of elements in the number of dimensions. So if I have, let's say, 2 entries for my embedding, it divides it by square root of 2. If I have 1,000, it divides by the square root of 1,000. Why? Because I don't think there's a reason. I think they just try to keep the numbers not too big and not too small. So they divide that by that so that the training is easier. It's more of a heuristic, but just to let you know, ChatGPT uses this. And when you see the formula for attention, there's this divide by square root of decay. And that is why you, the similarity metric they use. And this KQ here is exactly a dot product. This is dot product divided by square root of decay. And the softmax is the one that makes you move in a line, because softmax, the two numbers add to one, so you're moving in a line. I'm happy to elaborate on this anytime you want, if you want to ask me like at the end. But basically this formula over here is the gravity formula that moves. So just to give you an idea, right? Like if you have a high similarity between apple and orange, then it pulls it a lot. And if you have a low similarity like apple and truck, it doesn't pull it very much. What it's really doing is it's saying my new apple is going to become some percentage of my old apple plus the remaining percentage of orange. And if you have an apple moving towards a truck, then it's most of the apple percentage plus the remaining percentage of a truck. The higher the similarity, the higher this number is that you're adding of the other word. And that's encoded in this formula over here. As I said, this is as far as I'm going to get with this formula, but I'm happy to elaborate it if anything. We're going to talk a lot about this K and this Q. Let me see if I have some questions that I didn't address, because we're going to switch topics a little bit. Body models or embeddings learned for individual words. Yeah, Nermin has a great question. During the training of embedding models, are embeddings learned for individual words, for sentences, or does it depend on the context? Great question. Sometimes they're learned for sentences. You can have like sentence embeddings, where like sentences like, hello, how are you? And hey, how's it going? Are close by. But actually, the transformer models do it for individual words, and then they join them using attention. We'll get to that. Vikramit says, calculating attention for all the words in a context seems expensive. Is that why context windows are a limiting factor for generators today? It's expensive, but at the end of the day, is linear algebra. So it's multiplying matrices. So it's expensive, but manageable. And it really helps. And we'll see when we get to the architecture of the transformer, we'll see that this attention thing really helps. Xiang says, what about small angle but 2 items far away? I think that we talked about it. Yeah. Dot product captures magnitude and direction, says Robert. Yes, absolutely. Was there research that showed the method is better than just simple dot product? Great question, Robert. I don't know. I think what happens is when they were writing that paper of attention, the numbers were probably getting out of hand, like too big or too small. Training a neural network with a number that's too big is like throwing a wrench in a machine, or with a number that's too small is like doing nothing. So I think that decay just keeps them in check. At least that's what I've sort of asked everybody and researchers, and they seem to agree on that. A lot of machine learning is that, like, we tried that and it worked and we just let it, we didn't touch it. So I've been talking about similarity, but actually similarity is way more complicated than it seems. Because gravity is complicated, right? Like you don't just pull the same. Big planets pull more, small planets pull less, and the same thing happens with similarity. So there's this thing called the keys and query matrices, which appeared here. I'm going to tell you for the next sometime what K and Q are. They are matrices. I'm sure everybody here knows what has seen matrices, and maybe you've seen it the way I learned them, which is an array of numbers. And I don't like matrices as array of numbers. I think it's sort of the least pretty way to look at them. I see it as looking at a book as an array of letters. You don't look at a book as a bunch of letters together. You know that these letters form words, and the words form sentences, and the sentences form stories. And when you tell me about a book, you don't tell me about the letters, you tell me about the story. Same thing. When I tell about a matrix, I tell you about the story that it tells. And matrices tell a bunch of beautiful stories. And my favorite is linear transformation. So what's a linear transformation? Let's say I have an image, okay? I can transform it in several ways. For example, I can rotate it. I can stretch it in any direction. These are all matrices, 2x2 matrix, 2x2 matrix, 2x2 matrix for a different stretching. And there's another one slightly weird, which is a shear, which is if I take the book, fix the bottom and push the top, it becomes a parallelogram. Anything that takes a square and turns it into a parallelogram is a linear transformation, okay? Anything. That's, if you take parallel lines to parallel lines, that's a linear transformation. And that transforms the whole plane, because you can imagine using this dog to tessellate the plane and then using this parallelogram dog to tessellate the whole plane. So it just goes from the plane to the plane. This is a 2x2 matrix. Which one? I don't know. But every matrix is a linear transformation. And for 3x3, same thing. It'd just be like taking a cube to like a parallelepiped or whatever it is, right? And you can think of linear transformations as a matrix, like a 1,000 by 1,000 matrix, something that takes 1,000-dimensional space and like parallelograms it all the way into another one. But parallel lines need to go to parallel lines. Some transformations are linear, some are not. So this is my picture. And I use some software to turn it into linear transformation. This is linear transformation. Squares go to parallelograms. And these are not linear, right? This keeps lines, but they don't make them parallel. And this one turns it into like, you know, it makes an eye bigger. If you make a square into a circle, that's not linear transformation, right? So we're going to talk about a lot of this today. So remember this. Linear transformation turns squares into parallelograms, and nonlinear can do a lot of other weird stuff, okay? These are always matrices. Linear transformations are matrices, and the others are just messed up functions, okay? So the question that what we're gonna do is we're gonna take an embedding, for example, this embedding, and do a linear transformation to turn it into another embedding linearly. So it's parallelograms, right? Question, if we have a perfectly well-defined embedding here that some scientists created with a lot of computers and a lot of data very carefully, why would I want to mess with it? Why would I want to stretch it around, right? I'm going to give you 3 reasons why you would want to do that. The first one is that not all features imply similarity, believe it or not. What do I mean by that? Well, I'm going to ask you a small quiz. This is not a quiz as in like right answer, wrong answer. This is a conceptual quiz, okay? So I have an embedding where to the right, I have the size, okay? So as you can see, the little bunny is smaller than the elephant. As things get bigger, they move towards the right. And in the top, in the vertical is animalness. So non-animals are here and animals are here, okay? So embedding with 2 features. Which one do you like more? And obviously, there's no right answer here. There's one that I have on my own opinion, but I'd love to hear which one do you think is better of these 3? And whatever logic you want to use. This is a very open question. So if it looks like I'm giving you not enough information, it's because I'm not. Something like 3, like 2, like 2, 1. There's arguments for everything, right? If you want to write an argument, see, it says something very important, which is depends on how much you weight each feature, right? So in the first one, I put size and animal as the same. In the second one, it seems like I'm downgrading size. I'm saying size is less important. And in the third one, I'm upgrading size. I'm saying size is all that matters, right? I see a lot of great answers. Nermin says 2 because we can see how elephant is bigger than the rabbit. Yes. You can apply the weight more fairly after the fact. 1 is more tunable. Wow, a lot of great answers. Yeah. As I said, all work. But I'm gonna tell you why I think number 2 is my favorite here. And the reason, and actually the third one I like less. But as I said, this is just because I have one reason, but there's a million reasons why they're different. And the first one is so. Why? Because of similarity, right? What is more similar? An elephant and a rabbit or an elephant and a truck? Right? Exactly, and he says animals. In my head, at least semantically, if I'm talking about an elephant, I may talk about a rabbit, but I'm not going to bring up a truck. You see what I mean? Maybe if I'm filling a ship with things, I need the elephant and the truck to be similar because they're weighed the same. But if not, jumbo truck, I love that. But in my head, a conversation of elephants is more likely to have a bunny than to have a truck. So in my head, I want these two to be more similar. So embedding 2 is better, right? Does that make sense? But I like that we had a disagreement. This will come up later, the fact that we have a disagreement and how we fix it, because things are very conceptual. So, but let's say for now that I want to turn my embedding into this. And this is a linear transformation because the square went into a parallelogram, right? That's a linear transformation. And I made a better embedding. Right? By stretching, compressing. A way to look at it is, again, with Tinder. You can explain everything with Tinder. If I want to have a questionnaire, and I have questions like long walks on the beach, and they have the same answer, pineapple and pizza, and they have the same answer, but they disagree on thoughts on marriage and kids. Are these a good match? Thumbs up, thumbs down, give me a... they're not a very good match, right? But they answer 2 questions out of 3, but it's this question that matters. This question is louder than the other 2, right? And I can just weight each one of them, right? I can say this one I multiply by 10. This one by, let's say, 1, because pineapple and pizza may still be a deal breaker. And let's say that this one is okay, they disagree on. So I'm basically weighting some features more than others, which is what I did with size and with elephant, right? Like I multiplied size by smaller and multiply animal by bigger because I want some questions to weight. So I don't have a questionnaire, I have a weighted questionnaire, and that's a linear transformation, and that's a diagonal matrix. If you think about, if you like matrices, if you don't like math, don't worry about anything I said for matrices, but if you do, it's exactly a diagonal matrix. So that's reason 1. Sometimes features speak louder than others. Reason 2 is that sometimes you have to combine features. Okay, how you combine features? Well, let me give you another example. Here we have an embedding where we have 2 students. They're very good students, Aisha and Beto. And you can the embedding tells you what's your favorite subject. It could be math or it could be physics. Turns out that Aisha's favorite subject is math, so she gets a 1 in math and a 0 for physics. And Beto's favorite subject is physics, so he gets a 1 in physics and a 0 in math. And here's where they are in the embedding. 1 for math's your favorite, 1 for physics your favorite. And now you're going to help me out. Which of these 3 embeddings do you prefer? Which one looks more useful? 1, 2, or 3. And don't be afraid of saying the wrong one, because there's no right or wrong. There's the one, I think, but any argument works. So don't try to guess what I have in my mind. Try to tell me what you're thinking, because that's cool. I see a 2, I see a 1. 1 has same weight on both features. I see a 2, I see a 3, I see a 1. I love this. I love this because it shows that language models will put different measures on different embeddings, and we have to one day, or one day means in like 10 minutes, actually deal with this disagreement, right? But for the moment, I will tell you that I do system similarity angle between, yeah. To me, the best one is this one, okay? And the worst one is the third one, but only because of the reason I'll tell you. There's reasons for 3 to be good. I think that embedding is very unforgiving, because if I like math more than physics, I probably like physics too. And one day I saw something and I started liking physics too, and I moved from here all the way to here with a small change. This is unforgiving. I don't like unforgiving embeddings, right? It's too drastic. You made a small change and boom, you went from here to there. Things have to be nice and continuous and smooth. So I like this one better because these 2 kids are more similar, right? If one likes physics favorite subject and the other one likes math as the favorite subject, I think in my head they're more similar than different. So I like embedding 2. How do we turn this embedding into embedding 2? Well, but as I said, this is an argument if you're talking about research in math or physics, which are different, and this is another argument. So always everything's an argument, but I want these to be too far. I want them to be closer. This is what I'm going to do, okay? I'm not going to scale each feature like we did with the previous example. I'm going to combine them. So I'm going to say, you know what? If you like math, you get your 1 for math. But I'm going to say, if you like math, I'm going to say that at least you like physics 50%. So I'm going to add 0.5 for your physics score. And the same thing, and that moves her up here because her coordinates are no longer 1, 0. Now they're 1, 1.1, 0.5, right? And the same thing for physics. If you like physics, you get your physics score, but I'm going to give you 50% of math. Moving him from the coordinates 0, 1 to the coordinate 0.51, right? And so now they're closer. So what does that do for the linear transformation? Well, it takes the math and keeps it as math and adds 50% of physics. Physics is vertical, getting this edge over here. And then it takes the physics and adds 50% of math and it pushes it here and gets this edge. So this square goes to this parallelogram and boom, we have a linear transformation where now these two are much closer. Okay, so memory check. The first was that some features need to be scaled or multiplied by a big number or a small number to add similarity. The second one says sometimes I need to add 2 features or 3 features or 4 features because that speaks louder. You know, math plus 0.5 physics speaks louder than just math or just physics, right? So I need to combine them. Those are the normal ones. The third one is the weird one, okay? The pool doesn't have to be symmetric. So far, I've been saying that word 1 pulls word 2 and word 2 pulls word 1 based on how similar they are. I lied to you. Because in reality, some words pull stronger than other words in the same way. Like sometimes word 1 pulls more, word 2 more than word 2 pulls word 1. Kind of like planets, right? Like it's the same force, but Jupiter kind of pulls the moon more than the moon pulls Jupiter because of the mass, right? So words have the same problem or the same feature. Help me out. I have the word fisherman and the word net. Which one do you think pulls the other one more? Does fisherman pull net or does net pull fisherman more into a conversation? Good job. Everybody says fisherman pulls net. Good job. Amazing. Yes, fisherman pulls net more than net pulls fisherman. Why? Because I think you have the logic very, very well there. If I'm talking about that, yes, Felix's other objects are used by the fisherman. If I'm talking about a fisherman, then the net is likely to come up in the conversation. But if I'm talking about a net, I could be talking about all kinds of nets, the internet, a badminton net, a tennis net, a network of people. So if I say net, I'm not so likely to say fisherman. Maybe I will, but maybe I won't. Okay. Think about this. There's a movie called The Fisherman. That movie contains a net. There's a movie called The Net. Believe me, there's no fisherman in that movie. Does that make sense? There are other examples, right? Like if I say football and match, right? Which one pulls more? Oh, and I typed it in Portuguese because last time I gave this talk, it was to Brazil. Football pulls more, right? Because if I say football, I say match. But if I say match, I could be saying about other things. What about drink and Coke? Coke pulls more, right? Because if I say Coke, I say drink. But if I say drink, I could be talking about a lot of other stuff that are not Coke. So it's like gravity, but backwards. Because see, check this out. It's the small world, the one that pulls the big one. If I have a very popular word, that word gets pulled in all directions, right? Whereas if I have a very obscure word, it gets pulled into conversations. If I have a very obscure word, it doesn't get pulled anywhere. It just stays there and pulls other words to it, right? So attraction is not symmetrical, yeah? So for example, I have 2 people. Let's go back to Tinder, okay? And let me show you why dot product normal doesn't work. If you have 2 people on Tinder and they both answered a bunch of questions, and they answered the same on all the questions, you could be like, well, you know, these 2 should get married. But that's not how it works, right? The way it works is you have some features of a person that are what they want in a partner and others of what they offer. And you can't just match one by one here. You have to match what they want, what this one with what this one offers. And that tells you how attracted this person is to this one. and then backwards, what this one wants with what this one offers, and that tells you the attraction in the other direction. And there's no reason these two arrows have this to be of the same thickness, right? So the same thing happens with words, okay? In my embedding for fisherman, I have a lot of properties of the word fisherman and the word net, and I don't want to match them one by one. I want to match the features that pull other words, which are going to call the keys, with the features that get pulled by other words, which I'm going to call the queries, and that tells you how much fisherman pulls net, and vice versa. When I want to see how much net pulls fisherman, I match these with this, okay? So we have a small problem because we have one similarity. If I mess with this embedding into a linear transformation, I end up with one similarity and only one similarity, right? And I want that because I actually want two of them. I want to have a pull in one direction, a pull in the other direction, but then I'm in a bit of a pickle here because similarity is based on how the distance or the dot product or whatever, but it's symmetric, right? Like if I'm 5 meters away from you, you're 5 meters away from me, I can't just say I'm 5 meters away from you, but you're 7 meters away from me. That's impossible, right? So one embedding is not going to cut it. If I need two similarities, then I'm going to use two embeddings. So one embedding, one similarity, two embeddings, two similarities, okay? And how is that going to work? Well, I have one embedding for the keys and one embedding for the queries, and I'm going to mess around with each one of them separately, independently. These two don't have to be the same for the same reason that the similarities don't have to be the same in both directions. And then this is going to look a little magical, but I will promise I will elaborate. I overimpose them. And when I want to know how much fisherman pulls net, I don't look at fisherman and net. I look at key fisherman and green key fisherman and orange query net. And that's how much it pulls. They're very close. Strong pull. And I want to see how much fisherman pulls, how much net pulls fisherman. Then I look at the key green net and the orange query fisherman, and those are far, so it's a weak pull. So this looks magical, but you can see how two embeddings is able to break that symmetry, and you have one pull that's stronger than the other one, right? Again, if anything doesn't make sense, then definitely let me know. And Fabiano likes Portuguese. I like football. Are you Brazilian or Portuguese? Let's see. So I'm gonna do a numerical example of this, and I like this example not because I'm there, but because Taylor Swift is there, and I'm a huge Swiftie. Okay, I'm a huge fan. I know all the songs. I go to all the concerts. Help me out. Who do you think pulls the other one more into a conversation? Do I pull Taylor Swift, or does Taylor Swift pull me into conversations? Be honest. I can take it. I think, let's see, does Taylor pull me or do I pull Taylor? There's both. Yeah, I think it's, I'm gonna go for I pull her more for one particular reason, that it's that if she pulls me much less, even though she's the more popular word, should be Jupiter and I'm the moon, but I pull her, right? Because think about this. If there's a conversation about me, two people are talking about me, what do they say? They're gonna be like, oh, where's Luis today? Oh, he's probably at the Taylor Swift concert again. So she comes up in my conversation, right? And Felix says, yeah, it's because I know her and she doesn't know you. So I pull her into conversations. On the other hand, if two people are talking about Taylor Swift randomly in the world, they're probably not talking about me. Let's face it, right? So I pull her, I'm the fisherman, and she doesn't pull me. She's the net. She's the more popular word. Popular words don't pull so much. They get pulled into conversations, right? So let's throw in some numbers and see what it means to be pulled in terms of the dot product, right? In my embedding, let's say that my embeddings are always very nice and optimistic. This one has two features. Do you like pop music? And do you make pop music? So where am I in this? Well, I like pop music, but I don't make it. So I'm at 1, 0, right? 1 for like, 0 for make. And she likes pop music and makes pop music. So she's a 1, 1. Now, if I were to say how similar are Taylor Swift and I I would just take the dot product, 1 times 1, 0 times 1, and then I'll be like, well, we are similar unit of 1. Our dot product is 1. But that means nothing, because the fact that we both like pop music doesn't mean anything, right? It doesn't mean I would pull her or she would pull me into conversation. We need to modify this dot product. And how do we do it? Well, we have that one of these features is the key, the one that pulls into conversations, and the other one is the puller, the one that gets pulled. Which one do you think is the key? Likes pop music or makes pop music? And which one is the query? Help me out. If I like pop music, do I get pulled into conversations or do I pull other people into conversations? So makes pop is the key or the query? Makes equals key. I always get confused with this. Yeah. If I yeah, I need to reveal the answer because I always get confused. Key is likes pop music and queries makes pop music. Why? Because if I like pop music, then I talk about artists and I bring them into conversation. So I'll talk about The Weeknd or Beyonce, right? That's the key. I bring them into conversations. Whereas if you make pop music, you appear in other people's conversations, right? Because a lot of people like these Swifties are going to talk about Taylor Swift, right? So the key is the puller and the query is the pulled. And in here, likes pop music is the key and makes pop music is the query. So we're gonna bring that into the math. What we need to see how much I pull her is not the dot product, is not 1 times 1 and 0 times 1. We need to match my key, which is this one, to her query, which is this one. And that's the dot product we want, 1 times 1, right? And then you get 1, which is a strong pull, right? Now, this dot product, I had 2 features and I brought it down to 1. But if you had 1,000, let's say you bring it down to 100, you're like, these 100 are the keys and these 100 are the queries, and I need to do a dot product here instead of here, right? So if you want to know how much she pulls me, then we look at her key and my query. And because she likes pop music, but I don't make a pop music, then this gets 1 times 0, which is 0, which is how much she pulls me, right? So we got, basically, we got the two. And if you want to look at it geometrically, here's the key embedding and here's the query embedding. The key embedding is just everything goes to green, and the query embedding is everything goes to orange. So I just project that down. In here, we both like pop music. That's why we're in the same place. And in here, I'm going to put it here and rotate it. She makes pop music and I don't make pop music. So now if I want to know distance or angle or dot product, how much I pull her, then keys pull queries, right? So how much I pull her? Well, my key and her query are pretty close. So there's a strong pull. How much does she pull me? Well, her key and my query are not very close. Okay, so that's how you break the similarity. How are we doing there? Is similarity sort of more clear why key query matrices appear and what are they trying to break? Give me a thumbs up. Yeah, perfect. So let's get to a couple more things, because do you remember we had a disagreement here? Actually, let's say that we had a disagreement here, right? Like we had this one, and I said, I kind of like this one more, right? But maybe Raja says, you know what, Luis, math and physics are very different from the research perspective. So I kind of want them to be farther away. And what can we do? Well, we can say, hey, 2 heads think more than 1, right? Like we agree to disagree. And actually a bunch of us disagreed and said, hey, I like this one more. I like this one more. That's perfect. That's perfect. Because we're going to have 3 different heads of attention. Okay. Head 1, head 2, and head 3. And that's going to give us multi-head attention. So basically, what we have is a lot of key query matrices, okay? And one big head that's going to decide when to use ones more than the other one based on context, you know? So sometimes, let's say you're in a university career fair, you need math and physics to be more similar. So it puts more attention to this. It puts a bigger vote. Sometimes you're going to have this in a scientific conversation, you need math and physics to be more different. Or in other conversations, you need to combine them. So they have this sort of head thing going on. Sorry, let's skip a couple things. So that's basically So that's basically what happens in the, sorry, I got a little messed up here. So basically what happens is that, right? Like here's when you have the head of attention that decides for what context, which key and query to pick more than others, which embedding. So you always have a lot of these embeddings. You don't have just one transformation, you have a lot of these. And why does this work? Because in machine learning, teamwork normally works, right? Like if you make an algorithm take several copies and do a bunch of things, you'll find that it works like a team. It starts a mixture of experts in neural networks. It starts some embeddings start picking up the slack of others in some topics, and in others, other embeddings start being stronger, etc. So this tends to work very well. So I think the original paper has like 12 heads of attention. That's 12 key query matrices that work well in different contexts. Maybe in science, this one works well. In sports, this one works well, etc., etc. So that's what we're going to talk about, the key and query matrices. But now we're going to talk about the value matrix, which is also important. The value matrix basically is a little bit more abstract. But in this one, let's say I have my embedding, and the key and query matrices are the ones that tell me how words pull each other with gravity, right? But I still need another embedding that's optimal for generating the next word. And that's where I do the movement. So for that, I have the value matrix. I know this is a little abstract and it's not super clear, but if you imagine the numerical, let's say these are all the features of an embedding for Taylor Swift. Some of them are keys because they pull other words. Some of them are queries because they get pulled, but there are others that are the more important to talk, okay? When you're coming up with the next word in a conversation, maybe some of them don't matter. And let's say that they are pop music, let's say that they are Grammy winner, and let's say that they are musician and artist combined. So the value matrix that does it. The key and the query matrices take care of when words are similar or not. The value matrix takes care of extracting the features that are more important for talking. Okay, that's pretty much it. And so now we've seen the whole attention, right? The key matrix picks features that pull other words. The query matrix picks features that get the word pulled, and the value matrix picks features that are useful for talking. So the attention mechanism is basically that, right? Like you have this part calculates the similarity, and this part moves the words around. And when you have more heads, you basically have a bunch of different embeddings that are combined using this sort of smart head over here. And that is what happens when you look at the actual transformer architecture. It has this sort of strong heads of attention here. So we've managed to do this one. This is the most extensive one, by the way. How are we doing with time? We want to break at the middle, right? At like, I'm at 1:30. What is that? Like 10? Should we break it around the half hour? We do a little bit of feed-forward network and break at the half hour. Sounds good? Okay, so the next thing I'm going to tell you is the feed-forward. And by the way, thumbs up, thumbs down. You've seen neural networks, and I will sort of give them to you from scratch because I want to give you the way I look at them. Okay. But feel free, if you have a knowledge of neural networks, to sort of interpolate this with the knowledge you have. I'm just going to give you my own view. This is how neural networks appear. I don't really like them, and if this is the first time you see them, that's fantastic as well. So either way, it's a win-win. I'm going to tell you more about the neural network part of the thing. So let's say that let me review some things. I think most of you know this, but if I have a one-dimensional space, that's basically one number in a number line, right? A two-dimensional space is points in the plane with two coordinates, for example, 3 horizontal, 2 vertical. Three-dimensional space is just points with 3 coordinates, the street, the avenue, and the floor. And a 1,000-dimensional space, a 100-dimensional space, it's hard to picture, but you just have, like, let's say, every point has 100 coordinates. Okay, so where do images live? We're going to talk a little bit about images. Where do images live? Like this pixelated image here with zeros and ones, It's 7 by 6, so it lives in 42-dimensional space, because what I do is I stack all these columns together, and I live in a 42-dimensional space. Somewhere over here is this image, right? MNIST lives in 28 by 28 dimensional space because it's 28 pixels by 28. The CFAR data set, which is colored images of 32 by 32, lives in this dimensional space because it's 32 times 32 times 3 for blue, green, yellow. Where the words live, well, like the simplest embedding, the one that the original one before embeddings got smart, was basically saying, if you have 1,000 words, we have more than 1,000 words, I'm just going to call it 1 for the word that I'm looking at and 0 for everything else. So I live in 1,000-dimensional space. Of course, we have better. We have embeddings, which, let's say, bring every word to 1,024 dimensions. That means that words live in 1,024-dimensional space. So let's just remember that even though all my spaces are 2-dimensional, every time I do something is 2 dimensions or 3, because I can only imagine those. But picture things happening in 1,000-dimensional space. So let's talk about neural networks, right? Like, how do you, let's say, classify images of cats? Okay, this is like 10 years old stuff when we started recognizing images. Well, if data was nice, and I put them in an embedding, an image, and everything here is cats and everything here is not cats, then I just come up with something called a linear model. A linear model is a line. I cut it with a knife. All the cats are here and all the non-cats are here. However, life is not that nice. Data sets are not that nice. And if I want to separate the cats and the not cats, I kind of need a really twisted line, which is a non-linear model. Okay, that's what neural networks are going to help us with. Now, drawing a bent line or a bent boundary is really hard. And so we take advice from this kid. Who knows where this is from? What's this reference? Help me out. The Matrix, right? You can see Neo here. There is no spoon. Exactly. That's good. So Neo is trying to look how the kid bends the spoon, and the kid said, in very British accent, he says something like, don't try to bend the spoon, just try to bend yourself instead. And then he starts bending the spoon. We're going to take the advice from the kid. Let's not try to bend the line. Let's try to bend the space instead, using nonlinear transformation. So remember that a linear transformation takes squares into parallelograms, and a nonlinear one takes squares into anything, right? Just bends it. Like for this, I just took a software that bends it, that modifies images, and I started pulling points apart. That's a nonlinear transformation. They're more complicated. And now we are going to need nonlinear transformations, because what we're going to do is take this space and bend it in a way that now all the cats are on one side and the non-cats are on the other side. That's a neural network, okay? And this line, if I remember how I bend the space and I unbend it, becomes this twisted thing over here. So it's better to have a line in a bent space than a bent curve in a nice space, right? And that's what neural networks do. They basically find the perfect way to bend the space and maybe put it in higher dimensions, who cares, so that we can cut, and this cut was there. Excellent. I'm glad you're liking the analogy. And then at the end, there's crunching it down, which is the softmax. I will talk about the softmax later mathematically, but basically, once I organize the space like this and the cats are on one side, I can bring it down to a line and put all the cats here and the non-cats here. And then this cut becomes this cut, right? Like once I organize them, I can just put them in a line with one little mathematical operation that will get to it. And so in other words, the neural network just finds the best way to bend space and then bring it down to a little segment in such a way that when I cut this segment, becomes this cut that could be it could be a plane. I just cut it with a knife, and that becomes my complicated cut. That's the essence of neural networks, okay? And that's what this is saying. Here's my input. My input is here. My bending space part is the part in the middle, and this last part is the softmax that turns it into a line. Okay, now what if I have more inputs? If I have more inputs, cats and dogs and other stuff, well, I could just find a neural network for the cats and a neural network for the dogs, bend them in different ways. so that one captures one cut and the other one captures the cut that splits the dogs. But that's actually not what we do. The magic of neural networks is that the same neural network can be found, it can be trained for both. So one that puts the cats in one corner, the dogs in another corner, and this becomes the cat and the cut, and this becomes the dog cut, okay? And you can do this with as many inputs as you want. Obviously, I'm too optimistic here. I could get a dog in the wrong side, who cares, right? But for the most part. And so what I end up is with different softmaxes. Check out, remember this picture is a little messy, but basically there's a cut for dog, cut for cats, and a cut for other stuff. And I can bring it down to using the softmax to a segment where my stuff, sorry, this should have been flipped. I'm sorry about that. But this one separates the stuff from the animals. This one separates the cats, and this one separates the dog. So imagine this, right? I have my data. I bring it into a big, messy, nonlinear thing. And then for each one of the classes that I want to cut, I bring it into one different segment by looking at it from a different angle. Okay, if anything's not clear, do let me know, please. But I want to have this image because that's the image that I want to have for the transformer, for ChatGPT. Xiang says, is each cut way a model? So think of this. To get the first cut, I look at it from this perspective, where like the stuff here is 0 and the stuff here is 1. To get this cut, I look at it from the perspective where the cats are on the right. You know what I mean? Like I just have to look at it and bring it down to a line. I will explain the math in a bit. Not too deeply, but I will talk about it. But if you imagine that basically, if I start with messy data in a nice space, I turn it into a huge messy space, but with organized data where things are in each corner. And then for the classes that I want to do, for example, the cats, the dogs, and the else, I can bring it down to a little segment where the stuff I need is on one side and everything else is on the other side. All right. So it's more of a mental picture. How do we do this, right? How do we do this? Bend it like Beckham thing, like crazy, right? Well, we do it step by step. We're gonna basically build these things with little building blocks, okay? And we're not gonna get to it's like building things with Legos. You may build, the Statue of Liberty with Legos. You don't get to exactly the Statue of Liberty, but you get really close using enough Legos, right? So we're gonna use linear and nonlinear transformations, and we're gonna alternate from linear to nonlinear. But the idea is that you slowly start bending the space. The first layer of the neural network bends it a little bit. The next one bends it even more. The next one more and more and more. And the last one brings it down to a segment where all the stuff is here in one class and here in the other class, okay? And the number of nodes is the dimension. So here I started with 2 dimensions, 2 nodes. I went to 3 dimensions, 3 nodes. If I had 100 nodes here, it means I'm putting in a 100-dimensional space. And basically, this is how I create this monster of a space. I go 1 linear, 1 nonlinear, 1 linear, 1 nonlinear, 1 linear, 1 nonlinear. Each one of them is a layer of the neural network. Layers are composed of a linear map and a nonlinear map. Linears are nice. It turns a square into a parallelogram, right? They are nice. And nonlinear ones are ugly. They do crazy stuff. But I'm going to pick the nicest nonlinear map that I can think of. I'm going to pick a really simple one, and I'm going to pick the ReLU. Give me thumbs up or down if you've seen a ReLU before. Basically, the ReLU does the following. It's the most the simplest nonlinear thing I can do. So what's a linear thing? The function y equals x. That's a line. How do I get to a non-linear? I'm just gonna break the line and cut it, like, okay? And I have the ReLU function. It says the following: if you're a positive number, you're gonna stay the same. If you're a 5, you stay 5. If you're a 7, you stay 7. And if you're a negative, you become 0. So a minus 14 becomes a 0. That's very simple, but it's nonlinear. And that's the little building block that we're gonna need to turn this into a big nonlinear thing. So for example, this image is important to understand. This is, for example, a space that I bent, right? In a linear way. If I apply the ReLU, notice that anything that's positive becomes positive, and any coordinate that's negative becomes 0. So for example, this dog over here goes to 0, right? This one over here goes to 0, 0 because it's 2 negative coordinates, okay? So the ReLU basically takes this parallelogram and sends it to this little thing. That's nonlinear. It's simple, but nonlinear, right? This is what nonlinear does to me, right? Just only keeps the positive part and makes everything else 0. So every layer of my neural network is a combination of a linear map that takes squares to parallelograms and the ReLU. And with that, I can build anything here. That's an amazing theorem in machine learning, right? This is called the universal approximation theorem. With a bunch of linear maps and a bunch of ReLUs, I can build anything. Obviously, because ReLUs have corners, it's just going to look like corners, but I can get as close as I want. Is that clear, or do you want me to elaborate? By all means, if anything is not clear, I'm happy to elaborate. And I have about 5 more minutes of this, and then we go to a break, okay? So here's the neural network for classifying images, right? I have my original embedding, and here's my cat. And then it goes to a cat somewhere here, and then it goes to a cat somewhere here. And then in the softmax part, I have a high score for cat and low for dog and other, right? I'll get to ReLU in a minute, Sen. And if I have a dog, then that's gonna give me a high score in the dog segment, and low on the other one. Is if something else, it's just gonna have a high here and a low for this ones, right? So I have as many here as I have classes. I want to know if this image is clear or if there's any doubts, because if there's doubts, I can address them. If we understand this image, then we're gonna understand a transformer. Yeah. In the meantime, I'm gonna go back and because Sen asked the question about what is ReLU, right? ReLU takes positive numbers and keeps them the same, and negative numbers turn them into 0. So here, look at how it kind of turned everything that has 2 negative coordinates turns into 0, 0. Anything with 1 negative coordinate, like this cat, keeps the positive coordinate and makes the negative one 0. Okay, so that's the ReLU. It's obviously nonlinear, but it's as simple as you can get for a nonlinear function, right? It's just the little building block we need to nonlinearize this thing. Okay. Mohammed says, it's always true that each layer has one nonlinear and one linear transformation. Yes, it is. And sometimes the nonlinear one is sigmoid or tan H or something. I'm just going to talk about ReLU, but if you know other nonlinear functions, they work. Yes. There's lots of them. Yeah, I think gel might be another one. Okay, so super important. If this image is clear, this is a neural network, okay? Because this is how we're going to understand transforms. Now, I've talked about images a lot. Why did I talk about images? Because you can train the neural network to classify the images, and I can give it as many outputs as I want. Now, this talk is about language models, not image models. So we have to get to language models. So how do we get to language models? I need to find a data set to train this so that I can make the model talk. Well, let's make it talk, okay? I'm going to create a data set like this one, but for talking. So here's the thing. Let's say that I'm going to do something very simple. I open the page of philosophy in Wikipedia, and I'm going to create a data set. I'm going to teach the model to give me the next word after a word. Okay, so for example, the next word after philosophy is love. I add that to my data set. The next word after love is of. I add that to my data set. Of wisdom, wisdom in ancient Greek. Greek is asystematic. Okay, so I'm going to teach my neural network not to recognize a cat, but to recognize the next word in a sentence, and I fill this data set. So just like I had images and dogs, cats, and others, then I have words and the next word. So I'm going to train a data set to mimic this instead of this. How? Well, let's do ancient Greek, right? Now, pay attention to this. This is my word embedding. My word embedding puts the word ancient, let's say here. And in my neural network, this word gets modified. And then I have the softmax, I have a lot of classes. Before I had cat, dog, other. Now I have lots of them because there's as many as words. Okay, this is a key step. I have as many as words in the language. And basically, if Greek is the word after ancient, then when I look at the word Greek, it's going to have a high score and low scores for everything else. Okay, so just like I had the cat, you know, cat goes to cat, goes to cat, goes to a high number for cat and a low number for dog, then ancient goes to ancient, goes to ancient. It has a high number for Greek and a low number for everything else. That's a neural network that comes up with the next word in a sentence. Okay. Now, obviously, the next word could be many things, right? It could have ancient Greek or ancient pyramids. What does that mean? Well, that in when I look at Greek and pyramids, they have high scores and everything else has a low score. Okay. The problem is that this doesn't talk very well, because if you come up with the next word after a word, then you say hello, the next word is how, and how, the next word is much, because how much. And you end up talking like, hey, hello, how much obliged, because you now talk like Dory again, because you're coming up with the next word and you don't remember anything before. So you could do something called recurrent neural networks. We're not going to talk about them, but I encourage you to look them up. I can give you some resources where you have a bit of a higher context window. You're able to remember 3 or 4 words using a neural network that has some kind of like circular connections. And then you can talk a little more, right? Hello, how are you going to the, that still talks like Dory because it only has a really small memory. The good thing about transformers is that they have lots and lots and lots of memory. So here's how transformers operate, okay? Take a look at this. This is the key part. I'm going to use one neural network that talks. So at hello, it gives me the next word, how. And I'm going to replicate it for hello, how, are. I'm going to find the next sentence, the next word after hello, how, are. And I'm going to use the neural network 3 times. What is that word that comes after hello, the word after how, and the word after are? Okay. If the image is not clear, please let me know. And what I'm going to do is, this is not very good because I have the neural network that comes up with the next word 3 times. That's not good. I can also join them and I get the same thing, right? Like, hello, how are, get mapped into something here and get mapped into something here. And then the neural network tells me what's next after hello, it's how. But I haven't done anything, right? Because these are still separated words. I haven't been able to join them into a sentence. The neural network knows that there's a hello, that there's a how, and that there's an are, and that's it. We need to get better. So what do we do? To join these things in a sentence, here's where the magic happens. We use the gravity analogy. Do you remember the word gravity? So in each one of the layers of the neural network, we're going to use gravity. So here's what we do. We say, hello, how are, and we put them in our embedding just randomly. And we apply word gravity. So we make them gravitate towards each other the way we learned before. Then they pass to the next layer. And then again, we use word gravity. And then they pass to the next layer, and again we use word gravity. So by the time we get through 100 layers, we've done word gravity 100 times. Now these words are really entangled. Now it's not just are. Are has a lot of knowledge of hello and how, right? And so when I do the final step, then in reality, the word are carries a lot of knowledge of the other two. And so the neural network is able to find the next word in a sentence, because that last word now really knows about the other two because of this word gravity I applied. So in other words, a transformer is like a big neural network, except at every step, I apply word gravity to the words. Okay, I hope this was not, I may have gone a little abstract, but as long as the main idea makes sense, it's like a neural network, but I apply gravity at every step. And so the words really get soaked on each other's meanings, right? Like I used to have hello by itself. Now it's like hello, how, are, hello. They get really, really entangled. And that's how I add context. So at every stage of the neural network, I add context, add context, add context, add context. And by the time I get to the end, these words are good friends. You know, they're like buddies. I think we can break here. say 10 minutes. We got to the meat part of this, and then we'll get to a few other things like softmax, etc. We need a few of these, but these are much easier. But let's do, what do you say, 10 minutes? And if you have any questions, feel free to put them in the chat, and I'll just start the next part by addressing them. What do you think? Yep. Cool. All right. See you in 10 minutes. So that would be at PST 10:50, right? Hello again. Can you hear me? Perfect. We'll give people a minute to come back. Actually, while they come back, I noticed that a few things I answered, but there was one. See. If we have ReLU to approximate a curve, do we really need linear transformation? That's a great question, Vikramjit. Yes, we do. Yes, we do. We need, because otherwise ReLU just does ReLU and that's it, right? We need to modify things, then apply ReLU, modify things, like you modify things, then break it, linearity, modify again, break linearity, modify again, break linearity, and you can end up with any space you want, or approximate any space you want. So this is huge mathematical theorem, right? The fact that with just ReLU and matrices, you can create, you can approximate any messed up function, no matter what messed up function, you can approximate it with those. It's not obvious, right? It's the fact that neural networks work so well. It's why they work, because you can, there's no data set complex enough that you can't get to really closely using just ReLU and linear transformations. And as a matter of fact, a lot of functions work for that ReLU, right? Like if you know the sigmoid, if you know tan H, most functions that break linearity, actually the theorem says anything that's not a polynomial. So most functions that are not linear work for that activation function. Anyway, another one that we're gonna see is the sigmoid. So let me share my screen again. Also, there's a recurring question, and I don't know if Nabihas are you here? The question is if the recording will be shared.
Yes,
Or
the
Sanjay,
recording will
perhaps?
be shared with all the attendees on
Excellent.
next week.
Perfect. Okay, excellent. So that no pressure. I can't make mistakes now. He'll get down in history, be like that guy. Alrighty. Okay. So bending only happens. Yeah, definitely we'll edit it in post if I make some mistakes. So bending only happens with a combination of linear transformation and ReLU. We're saying bending and a straight line. Exactly. Yeah. ReLU just provides that little break that you need to use as many times as you want and get to everything. And that's the idea. Yeah. All right. Are you seeing my screen? No, I'm not sharing screen. I'm all over the place here. 1 second. Oh shoot, where I'm not in there. Sorry. Okay. Sharing screen. Okay, we did the hard part. Everything left is easy. We went through the complex mathematically. Now everything else is kind of like just bookkeeping. So let me tell you about, we have softmax, we have positional encoding and tokenization, and then we talk about other things in neural networks. But basically, yeah, the hard part already happened. What is this softmax thing that I talked about at the end, right? It's basically neural networks return scores, but scores can be positive, negative, can be anything, and the idea is to turn them into something between 0 and 1. Why would I want that? Why would I not just simply choose the biggest thing here, the most likely word? Because let's say that I have the sentence in the store, I bought an, and let's say I have 3 options: apple, orange, and elephant. Think of this as like thousands, but I'm only going to show you 3. The transformer will give scores, right? We'll give scores of 4, 3, and 1. Why? Because high scores for words that are likely. Probably I didn't go to the store and buy an elephant, so there's a small score here. Now, you don't want ChatGPT to answer the same thing all the time. You want it to be a little unpredictable, but not too much, right? So if you ask the same question again, you get different answers. Why? If it just answers the word with the highest score, because it turns scores into probabilities in order for you to sample. So how do you turn this 4, 3, 1 into probabilities to sample? I'm going to do the obvious. I'm going to divide by their sum. So I'm going to divide, I needed to add to 1. So I divide by 8 and I get 4 8s, 3 8s, and 1 8. And I just sample 50% of the time this one, 37.5% of the time this one, and 12.5% of the time this one. Makes sense, right? I'm not gonna hallucinate too often, and I'm gonna get answers with some probability. However, there's a problem here because scores can be negative, right? So if I have a negative here, I can't play this trick. So I get a negative probability. So what do we do? This is something you do in machine learning pretty much every time that you need positive numbers. And it's you take e to the score, okay? Why e? It could be 2 to the score, 10 to the score. Exponentials are always positive. So we use exponentials, okay? So e to the 4, e to the 3, and e to the -1. Exponentials are always positive, and also they're bigger if the number is bigger. So it's exactly what we need. And now I have big numbers, 54, 20, and 0.37. Look how small this is. And then to make it probabilities, I just divide by the sum, right? I divide by the 3 of, I normalize this, and I get 72%, 27%, and tiny percent here. So then I sample out of here, and I'm going to get apple most of the time, orange a big amount of the time, and never elephant almost. So that's what we do. And if I have 1,000 words, I just take the scores of the neural network, e to the that, and then divide by the whole sum, and I get a bunch of probabilities. And if I sample out of those probabilities, I'm very likely to get a word with high score, which means my answer is likely to be accurate, but not always the same. So I get to sound more like a person, because if it answers the same thing all the time, then sounds like a robot. On the other hand, you can mess with that with using temperature. You can change this base e to a higher number or a lower number in such a way that it becomes more predictable or less predictable. If you want something medical, for example, you want it to always answer the same thing. You don't want an exciting doctor. You want an accurate doctor, right? So you raise the temperature, you lower the temperature. If you want a poet, you want something unpredictable and creative, and it doesn't matter if it hallucinates a little bit. And so you would raise the temperature high. So temperature is always a knob that you can turn in a model, and it's basically changing this e so that it either gets the highest stuff with high probability or it evens them out a little bit. So that's softmax. Now let's go to tokenization. Basically, I may have slightly bended the truth, not lying, but bent the truth. Not the only thing we bent today, like those faces. So token, I really said words all the time. I always said words, but the model doesn't know what a word is. It uses tokens, and most words are a token. For example, write a story, period. Every punctuation sign is a token. Everything's a token. But sometimes you have 2 tokens for a word. For example, doesn't would be like doesn't. Like suffixes are tokens, prefixes are tokens. It's basically the best quotations way to break something down. If you want to try, OpenAI has an open tokenizer. You can just put the stuff, and notice that I said I'm learning a lot in the Data Science Dojo Agentic AI conference, and agent is a token. Dojo breaks it into 2, but for example, science, anti-disestablishmentarianism gets broken into a bunch of tokens with suffixes and prefixes. But for the most part, if you think that every word's a token, you can go about your day and do machine learning without a word, unless you work at a tokenizer. Unless you're the tokenizer person at an LLM company, then you need to care about tokens. And different languages have different tokens, and it's very important to tokenize well a language. Let me give you a sample of how to tokenize. This is a very old method of tokenizing called byte pair encoding, and it's basically joining letters when they appear too often. That's pretty much it. For example, hug, hugs, bug, and bugs. This is my entire dictionary of words. And I have 5 letters, H, U, G, S, and B. Question for you. If you had to join 2 of these letters into one unit to make things more efficient, which ones would you join? You are correct. Yes, Syed and Robert are correct. UG. Why UG? Because it's the pair that appears the most, right? HU appears 2 times. UG appears 4 times. So it makes sense to join U and G into one letter, and then I just have to type that letter, and I'm saving time. So I'm going to join UG, and I'm going to add it to my tokens. And I continue doing like that. So now from the tokens that I have, which one should I join the most? Well, it seems like every pair appears twice. So I'm just going to pick a random one and join hug. Hug is a token. And I keep going, right? So now I have ug and hug. And the next one is bug because it appears twice. So basically, if I just take the most common appearing pair of letters or existing tokens and join them, I get a pretty decent tokenization, right? There's better, but that's it. And why is BP important? Because it retains the information, right? Let's say I have the word laughed and the word walked, and I misspelled something and I get the word biscuit. I don't know what that is. But if I break them into tokens, this one got messed up. But I do know that at the very least, I'm thinking of the past tense of some word, right? I don't know what bisque is, but I know that bisque is the past tense of bisque, right? So tokens do give information, right? So yeah, something like that. And when I played with them, it didn't exactly do it, but you know, you get some information from tokens that kind of helps you out. As you can see, these are fast, right? Tokenization is fast, tokens fast. Positional encoding is really interesting. And actually, it feels like cheating a little bit, to be honest with you. But do you remember when we did this? That nowhere in the phrase, anything I did with hello, how are, was done exactly with how are, hello. Because nowhere in this business was the order of words even brought up. That's weird, right? Like, I could come up with that. I could reorganize the sentence and the neural network's like, yep, like you did nothing. So we need to somehow take that into account. We need to add something called positional encoding. And as I said, it feels like cheating because it's not doing anything intelligent with the positions encoding. It just does one thing, and then it trusts the neural network to learn what you did. Whatever, it worked. I don't question it, but I'm sure there may be better ways to do it. Let me give you an example. Let's say I say the sentence, no, it is good, and the sentence, it is no good. Those two sentences are the same words, but they're very different sentences, which is no good. But in the embedding, the model fits them in the exact same way, right? The model has no clue these two are different. It needs to know. So we're going to do the following. And as I said, forgive me because this is kind of sloppy, but I'm just going to take every word and move it around in some direction. But as you can see, the first word always moves to the right, the next one up, the next one left, and the next one down. And here, the same thing. So here I'm modifying the word no to the right, and here I'm modifying the word it to the right. So I'm doing something different. You see, I'm going to move them like this, and I'm going to move them like this. So here no goes to the right, but here it goes to the right because it's based on position. That's why it's called positional encoding, right? So when I move them, I get different stuff, right? And it turns out that that's all that really mattered, that it's different. We need two things, different and predictable. See, this sequence is predictable. Right, up, left, down, right, up, left, down. We can trust that a model that's smart enough will learn that sequence and reverse engineer it back to figure out the order. We have to trust the neural network. A lot of it is trusting the neural network. And that's pretty much all there is. Now, here's a problem. This sequence is periodic, and that's not good. So for example, this is what we would do. We would move the first word to the right, we pick some angle, and move the second word in that angle, the third word in that angle twice, and 3 times, and so on, and so on, and so on. But if the sentence is too long, eventually I get back to where I started, and the 11th word gets sent to a similar place on the first word. That's not good. So I don't want a periodic sequence, but I do want it to be predictable. And for predictable, I mean, for a computer, predictable kind of means periodic. If it gets too complicated, the model's already doing 1,000 other stuff. It needs an easy periodic-like thing. So what do we do that's periodic-like but unpredictable, right? Well, let's do the following, okay? Let's imagine that the embedding has 6 entries for the sake of argument, and we're going to take them in pairs. The first pair, we're going to modify them like this. We're going to move the first word here, some angle for the second word, third word, fourth word. We're adding, these are 2 numbers, right? These vectors are 2 numbers. I'm adding it to these 2 numbers, okay? For the second one, I'm just going to take a smaller angle for the third and fourth. For the 5th and 6th, I'm going to take a much smaller angle. By the time I get to the 999 and 1000, it's a tiny angle. So it's like wheels that are spinning, but the first one's spinning super fast, the second one's slower, the third one much, much slower, and the 10th, the 1000 one is barely moving, right? So this is periodic in nature. It's predictable, but oh, I did this again. When I do anything, I start getting balloons and stuff. Periodic in nature, but it's not periodic, right? You broke the periodicity, but it's predictable enough. This is the formula, blippity bloppity sign divided by 10,000 to the something, whatever. It does this, okay? So this is how we modify them in order to be predictable enough for the model to learn it, but at the same time, not periodic. And if you've seen this, this is positional encoding, and this is the wheel spinning, right? This one spins fast, so it changes color fast, and this one spin really slow, so they barely change color. So if you ever see this image, it's exactly what it means that the wheels spin for different elements in the embedding. Okay, so now we've done the whole transformer architecture. Congratulations. Let's actually go through the whole thing basically. So we have write a story, then it goes through tokenization, then this goes through the embedding. Then it goes through positional encoding, which modifies each word differently. Then this goes through a neural network that has some feed forwards and some attention steps of gravity in between. And then this gives you a bunch of scores for every word there is. And the softmax turns those scores into probabilities. And then you sample a word that always ends up being something almost always with a high probability. And then the word once gets added. So all of this stuff to add one word to your sentence. And then you repeat it and repeat it and repeat it and repeat it. So that we've ended section 2, which is basically all the architectural stuff. Yet you still make them talk, and they still hallucinate, and they still lie, and they still don't know how to say I don't know, and they're still full of faults and weaknesses, even after you do all this genius engineering with huge computers. What do we do to mitigate these weaknesses? In particular, we left this thing unanswered, right? Like, why are the jokes so bad, but the poems so good? After all that genius architecture with attention mechanisms and bleepity bloppity, it still can't tell a joke. I don't like that. So the question now, and I wonder if anybody thought about this when we said at the beginning, did anything of what we said about transformers makes a hint of why are the jokes so bad, yet the poem's good? Who can help me out? Poems rhyme. Yeah, that's a good one. See it, poems rhyme. I can rhyme with ChatGPT, but I can't laugh. I can't make someone laugh. Why? Actually, it's a funny story. Well, you think I'll tell you the story. I had to. This really bothered me, the jokes thing. And I asked a bunch of people I knew, and you know, there wasn't really a consensus on why it's so bad at telling jokes. I had to ask Jeff Hinton. Do you know Jeff Hinton? He's basically the godfather of AI, won the Nobel Prize in physics. And he lives in Toronto, where I live. So at an event, I said, please get me out of my misery. Why are the jokes so bad? And Robert, I think got the idea. Yes, it's pretty much exactly that. And he said, and Jeff Hinton said, the reason they're so bad is because they're thinking one word at a time. Yeah, Vikramit has a good point too. There's a pattern in poems, but not in jokes. So patterns are definitely something. So here's the thing. The problem is the fact that it speaks one word at a time. Okay? You cannot tell a joke one word at a time, but you can tell a poem one word at a time. If you tell me, do a poem about Data Science Dojo, then I'll just be like, Data Science Dojo, a great institution that teaches me AI. Something comes up. But if it's a joke, I can't, right? Like, what did the computer say to the table? I have no idea. I have to think. Because you cannot tell poems, you cannot tell jokes one word at a time. You have to think ahead, like Robert says, right? You have to think of a punchline and then work your way to it. You cannot do that if you speak one word at a time. Whereas in a poem, you can add the next word in the best possible way and somehow create a poem. So here's how I think of, here's how I think, and yeah, see, it mentions that it's similar to a limitation of predicting one word at a time. I think of ChatGPT as a car. What does a car have? A car have headlights and a rearview mirror. The headlights are for looking ahead and the rearview mirror for looking behind, and you can drive like that. Language models are like a car, except they have really low headlights, really low. They can only see like 1 meter ahead because you're generating one word at a time. On the other hand, the rear view mirror is huge. You can see kilometers to the back. You can see everything far away. And the fact that you have the attention mechanism means you can focus, you can do anything. So this is very strong, but this forward is very weak. And that's why understanding is easier than creating. And we talked at the beginning, right? Because you look at the back and you understand philosophy, art, music, science, everything. But when you start talking, generating, you only have one word at a time. And jokes have to be created this way because you have to plan your punchline, right? You have to plan your punchline ahead and get there. Whereas you can create a poem sort of looking back and be like, okay, I need to rhyme. Okay, I need to add a word for this. And you don't need to plan ahead. A good poem needs to be planned ahead, but a decent poem doesn't. And so, for example, if I'm in my joke and my poem, and I want to create the word here, unespied, then I think, well, these words would help me, and that's it. And maybe I want to rhyme or something, but I can always look back. On the other hand, if I want to if I want to put this word here, I had to start with something. And if I didn't set up the joke well, there's nothing I can do to fix it. This thing kind of fixed it, but as best as it could. But when it was creating the word why, it had to look here. You can't do that. You can only do the opposite. When I create this word, I can look back. Okay? So basically, think of this. When you tell ChatGPT to write a poem, it turns on the poetic muse to high, and it starts saying poetic stuff. And some poem comes out. Not excellent, but decent. On the other hand, if you tell ChatGPT to write a joke, you're turning up the jokester to high, and it starts trying to sound funny at every word. You can't tell a joke by trying to sound funny at every word. You have to hold back. You have to plan ahead. You have to invest in the future. Can't do that, right? So I think of this. A poem is like if you're walking in a garden and picking the most beautiful flower you can at every moment. You can do that with a low light. Pick the most beautiful word here. On the other hand, a joke, you have to find the tree far away and work your way through it. And that's not easy. So if you make a misstep somewhere, which you will likely do, you end up a really bad joke. So I like to think of a progression where joke is the hardest and poem is the easiest. And somewhere in the middle, there's a story. So for example, a series is not as hard. Like, I don't know, who watched Lost or Game of Thrones? They have something in common, which the series was very good, but the ending was terrible because they were writing it as they go. Lost, for example, I don't know who shares that they lost 6 years of their life, like me, watching that stupid series, because they were basically creating every chapter as they went, right? Like what ChatGPT would do. They never thought of the ending, clearly, and then they have had something and they couldn't even finish. On the other hand, a movie is harder, right? Because you can't have a good movie with a bad ending. You have to work your way to the ending. So I would trust ChatGPT to write a series before it can write a good movie. Okay? So think of it. The more you have to plan, the harder it is for ChatGPT. And that's why we have things like RAG and agents and everything to mitigate these problems and emphasize these strengths. So now that we look at it, every strength and weakness makes sense, right? Because you can talk about many topics. You can follow orders really well because you can summarize an entire chapter because it's put in on your rearview mirror and you can look at it. On the other hand, there's enough facts. Oh, I was translating from Spanish and I forgot to translate the sentence, but you know what I mean. So I'm going to give you now a bunch of strategies, the last one of which is agents, to strengthen, to use the rearview mirror in your own good and to mitigate that weakness of the light ahead. Okay. But the first one's actually not that. The first one I put fine-tuning first because it's slightly different. Fine-tuning is something you should do with every language model, and it's done by OpenAI and Anthropic and DeepSeek, and they always fine-tune their models. Why do you need fine-tuning? So let me ask you a question. Let's say you train a model that we train a neural network on the internet. Okay, you train it on the internet, and it learns to talk like the internet. That's like in the streets, basically. Like it's rough. The internet is a rough place. It's It's basically no man's land. And let's say I ask it, what's the capital of Brazil? So the answer would be Brasilia, but let's think, what could go wrong there? Help me think of ways where this could go wrong. If I say, what's the capital of Brazil? What are creative ways in which the model, if it just learns on the internet, would answer? And remember, it doesn't know it's answering a question. It just knows the next word. So if I just go on next word prediction, any ideas? It could say Brazil, for example. Let's see it. Yeah, it could say Brazil. It could say the wrong capital, right? It could say Lima, or it could say Buenos Aires, or something like that, Paris. Here's something interesting. It could say, yeah, B, it could say, right? It could just go for the next token. Let's see what, oh, I love it. Yeah, Kumar actually guessed what I was going to go for. What is the capital of Peru? If I ask it what's the capital of Brazil, it could answer what's the capital of Peru. Why would it answer in such a stupid way if I ask the question? Well, because there's a lot of quizzes on the internet, and a quiz has a question followed by another question, and the computer has no clue it's answering a question. It only knows the next word. And if the next word after a question mark is the beginning of the next question, the thing's gonna throw in a question for you. It doesn't know what it's doing. It's just a word. It's just a glorified WhatsApp autocomplete. What can you expect from it, right? So a lot of things can follow. A lot of things can follow a question that are not the answer, and that's a problem. And that's not something you fix with a linear transformation or a ReLU. That's something you fix outside of the model with data. Okay, so you need to give it lots and lots and lots and lots of data sets with questions and answers so that it gets used, that after a question, it answers its answer and not another question. It's basically just throw data at it. The same thing happens with commands. For example, if I say summarize this, it's not going to summarize it. How many times in the internet does the command is followed by the command being done? It's not necessarily, right? So you need to give it a lot of data sets of like a thing and then the thing done, a thing and then the thing done. Same thing with chats. You need to give it data sets. So you need to give it data sets of how you want it to behave. And that's like half of the work. Give an example. I used to work at Cohere, which is like a language model company, it has a chat button and everything. The first floor was employees, and the second floor was just annotators writing stuff like that, right? Like writing questions and answers. You get experts for everything. You need to do this. Otherwise, the model behaves the way the internet behaves, and nobody wants a model that behaves the way the internet behaves, right? You want it to behave like a person who's been educated. So I like to imagine as like, you learn on the internet means you learn to speak on the street, and then you curate, you train it with a lot of curated data sets. Question, answer, commands, chats, everything, math, physics, everything. And then if you have your own company, and you can always fine tune it with your own data sets. So if you have, for example, a bank or something, you just put all the PDFs, put all the files, and overtrain the neural network those so it gets used to it. So fine tuning is very important. Strategy 1, fine tuning. Always fine tune your models. Strategy 2 is very easy. It's a preamble. So let's say you ask the model, hi, I have a question. And it goes, what do you want? You don't want this for a customer service chatbot, right? What do? Well, here's something easy. You just put a preamble. You say, you're a respectful chatbot. You answer, blah, 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 blah. Check, make sure you ask another question before you hang up, blah, blah, blah. And then it just reads every time it reads your question, it just reads the preamble and then the question. So preambles are always important. If you're building a chatbot, always put a huge preamble with all the stuff. The next one is RAG, Retrieval-Augmented Generation. Thumbs up or down. Have you heard of RAG? So it's a popular thing. Maybe you have, maybe you haven't. Okay. So RAG, basically, here's the thing. I asked the model. I did this like the day after the US Open tennis final. I said, who won the 2025 US Open? And it said, I have no idea. It has not happened yet. Huh, how dare you? It just happened. So I didn't know. And then I clicked this button, search. This is DeepSeek, by the way, but you can do this in ChatGPT. I clicked the button, search, and then it answered correctly. It said read 2 web pages, and it even gave me links to click. That's RAG, right? RAG is basically saying, before you answer, look it up. Why is RAG so effective? Because if I ask a question, what's the capital of India, for example, and I expect the model to answer it with this little headlight, it's going to get it wrong. Maybe it'll be like Kolkata or something. Instead, if I put a really solid preamble and I say, hey, don't start yapping. Before you open your mouth, look up the answer on Google. And if you don't find it, say, I don't know. I tell it, say, I don't know. Magical words that ChatGPT cannot say. And then what it does is it looks it up and it puts all the results in the rearview mirror. So with the rearview mirror seeing the results, the question, and the preamble, then it's able to answer it because it's just answered by looking at the rearview mirror instead of looking ahead, right? So you're using this strength to mitigate this Achilles heel. And then it answers correctly. So RAG is very, very useful. What are the steps of RAG? Let me do a little workflow, which is what happens if, like, let's say, I don't know, somebody calls you or your parents call you and say, hey, I have a question, but the question is worded longer. I'm trying to remember what's the capital of India. I thought I knew it, but I'm not sure. We don't type that into Google, right? We have a skill that we've developed in the last 20 years, which is how to turn things into a Google search query, right? We turn it into a Google search query, and then we search it, and then we take all these and maybe more, maybe some more stuff came out, and with the question, the original question, the reworded question, and these all in the rearview mirror, we answer. Why is it so easy to reword a question? Because it's all in the rearview mirror. It's an instruction, right? Like, reword this into a Google query is very easy for a language model. On the other hand, answer the question is hard. So rewording into a Google query, easy. Answering, hard. That's why we use the search results. Normally, preamble, fine-tuning, and RAG make a good model. I would trust this because this one tells it what to do. This one fine-tunes it so it really gets it used to your data. And this one searches in a database before answering. So that's pretty good stuff. Let me tell you a bit more about reasoning models, okay? So reasoning models, when DeepSeek came out, it made a huge storm because it just reasoned really well. I started doing math with it and it started being really accurate. What happened with DeepSeek, okay? What was the thing? It's very simple. Very simple. Let's say I have two students and I give them a math problem. One of the two students starts writing frantically the solution. The other one wrote a page of drafts and then started writing the solution. Without knowing any more, who would you put your money on, student one or student two? Probably two, right? Probably two. Because at least planned what it was going to say. This is basically using this strength, right? If I say solve for x in this equation, the thing starts talking and it may get it right, but if it just starts talking, it may also get it wrong. It's using this weakness, right? If I give it a preamble that says, hey, before you open your mouth, write at least 10 pages of drafts and then read them to yourself, okay? Put them in your rearview mirror. So see, it's writing this draft is not easy. It may say 10 wrong things and one correct, but reading its own drafts is really good because the model's a much better critic than it is a creator. So reading your own drafts, you can tell that maybe the answer was here, okay? So you're using the strength of the rearview mirror to check your own work. You're being the model's being its own critic. That is a reasoning model. Now, you can get further. You can get one more step. What DeepSeek did is it used reinforcement learning to actually grade the draft. So it gave it an instruction to write the solutions using a bunch of steps. And then it checked every step. And it trained the neural network by telling it to write good steps at every moment. And the steps were checked with either the same language model or heuristics like compiling code, the math engine. Anyway, the fact is you train a model to write drafts and you check the drafts and tell it to write good drafts. And then you get a really good reasoning model. And that's why DeepSeek did so well. And the last strategy is agents. So agents is basically, I've talked about agents already because RAG is an agent, right? Why are agents? Why do I think agents are actually a good progression? Because technology always rhymes. Okay, if you remember the internet, those who were here when the internet started, it started as a text thing. It was just text. The pages were just text. Information, basically, textual information. Then it became multimodal. Images started appearing, videos, audio, all kind of stuff. Not just for input, output, but also for input. And then it became a tool. See, if 20 years ago they tell me I'm going to make a bank transaction on the internet, I would have thought it's crazy. Now all my bank transactions are on the internet, and I don't even question it. Same thing happens with large language models. They follow the same progression. So ChatGPT, first it started as text. You would just write text and it just replies text. Then it became multimodal. You can generate images. You can ingest an image. You can put in an image. It understands it. It creates videos, music, audio, everything. And then it's in the process of becoming a tool. Right now, it may be crazy to think that we're all gonna do everything using language models, but in the future, I see it like the internet, right? Like we're gonna tell it to write a bunch of emails, tell it to do a few things, it'll do them very naturally. Like we do a transaction on the internet, we don't even wonder about it, right? So language model, so let's talk about agents a little bit, and the lab is on agents. Agent has three things: brain, tools, and memory. RAG is an agent, right? Because what does RAG do? It first rewrites the question, then it searches in Wikipedia, and then it answers the question. I'm sorry, I think oh yeah. That's already an agent that's doing stuff, right? It's got the brain, it's got the functions that are rewrite the question, it's got the memory, which is what it said, and all this stuff. So it's basically the original agent is RAG. And so another thing that agents do is, for example, this. Let's say I ask how to do 3 + 7. Well, a model, think about this. A model doesn't really know math, right? Sorry, give me 1 second. I think I may have. Oh, sorry, I have this in order. No, sorry about that. A model doesn't really know math. So from reading the internet and guessing the next word, coming up with the fact that 3 + 7 is 10 is not easy. Maybe 3 + 7 = 10 appears many times in the internet and you got used to it. But if it's a bigger sum, maybe it never appeared on the internet. And maybe the rules of summation are somewhere hidden in the internet. And you could learn them from reading. But the fact is, it's not easy, right? It knows it's a number because it's used to, after a question with a number appears. But it's not easy to say 10. On the other hand, you can put a preamble that says, before answering, open the calculator and use it. So it just puts this into the calculator and then puts it in the rearview mirror. And with this and the question, it will answer correctly, right? So in other words, what do you think is easier? For a computer to look at this problem and say, I have 10 apples and I ate 4. How many do I have left? What do you think is easier? To say 10 - 4 or to say 6? For the computer. Right. See, it got 10 - 4. 10 - 4 is easy because if you think about it, 10 - 4 is language. If I don't know how to subtract, I can look at this and I'd be like, I have 10. I ate means I remove 4. 10 - 4. This is language. On the other hand, 6 requires math. For us, it's the same difficulty, but this is much, much easier for a computer than this. Much, much easier. And we have the calculator. So because 10 - 4 is basically something I can do by looking in the rearview mirror, but the 6 requires some thinking out of the box, right? Out of this box. So we have the calculator agent, which is I can look at the problem and extract the equation and then use the calculator for the equation and then answer the question. That's another agent, right? So as I said, agents are already embedded, right? Because if I say deep think, before responding, write drafts, that's kind of an agent. Before responding, look up the answer, that's kind of an agent, that's RAG. I could have a calculator button. Before responding, use the calculator, or a bank button, or a code button, or just a button for everything I want to do, right? Those would be like if I had agents in my chatbot. Or even better, I could have a router that checks out what kind of question you asked and does the right thing. If you ask a numerical question, it opens the calculator. If you ask a fact, it opens Wikipedia. Why is this router easy? Well, this router is a multiple choice question. What's the first thing we learned today? Multiple choice questions are very easy for the computer. So this router answers a multiple choice question. What app should I open? And then it opens it, okay? So I like to think of language models as a Swiss Army knife with all these apps that you can use. And sometimes you need more than one agent. So let me give you an example. You should try this by yourself, right? Just to see how weak these agents are, these language models. Try to get it to tell a story. And it tells you a beautiful short story. But then you say continue. And then you say continue. And then you say continue. And make it write something long. You're going to realize that the name of the protagonist changes in chapter 3 from chapter 1. This thing is like Dory with a little more memory, right? Like it still makes a lot of mistakes. It can be pretty consistent, but when things get long, it's pretty bad. So what do we do? Well, let's say I tell it to write a book. So believe me, by chapter 10, the thing goes nuts. And the characters change and everything. How do we make it write a good book? Well, let's say we have 4 copies of ChatGPT. The creative, the planner, the critic, and the writer. And each one has its own roles. So for example, the creative one writes the story in a small context window, in a concise, and then it gives it to the planner. Notice that everything is put into the rearview mirror. The planner, using the rearview mirror, it creates the chapters, okay? Gives it to the critic. Models are much better critics than they are creators. So this one is very easy for it to tell, hey, there's a discrepancy between chapters 1 and 3. Sends it back to the planner. With all this information in the rearview mirror, this one creates the chapters again. Sends it to the writer. The writer writes chapter 1. Okay? Sends it to the critic. And this one says, hey, you messed up here, etc., etc. That's a multi-agent system. Okay? And that's what works really well. Oh, that's a really good question. Is this what DeepMind did for the IMO? For the Math Olympiad? Is that what you said? For the International Math Olympiad? I don't know. That's a good question. At some point it must use agents and at least a very strong reasoning model. I know they did a lot of work for IMO problems. Now that I think I can get a gold medal in the IMO. But yeah, let me get back to you because I don't know exactly what they did with IMO. But check out the talks by Terry Tao. Terry Tao is the one that really has been pushing AI for doing math. Yeah. Okay, so where are the tools here, right? Like the brain is on every agent, right? It's the one that does the stuff and plans. The tools, what are the tools? Well, for the creative one is plan the story. For the planner is plan each chapter. For the critic is check consistency, spelling, critique narrative. And for the writer is just write the chapter. So any function is a tool. And the memory, well, the stuff that you're supposed to remember, right? The story, the chapters, the previous errors, the story, everything like that. And there's memory for agent and there's general memory as well. So there you have your agent. Now, just as a couple of more things before we get to the lab. Sometimes you have an agent and you have to throw in a new function and you don't know if you should create another agent or another function in the existing agent. How do you make this decision? Well, it's actually not that different from being a manager. Let's say you have in your team and you have a doctor and your new function is perform surgery. Well, you ask the doctor. But if the new function is check a lawsuit, you kind of have to hire a lawyer now, right? So the logic that you use for teams of people is the same logic you should use for agents. If you need a new function of an agent or a new agent. And now there's another agent that I'm going to show you on the labs, which is math or fact. This one does give it a question. It tells you if it's math or fact. If it's fact, it sends it to RAG. And if it's math, it sends it to the calculator agent. And then it answers the question. Why is this so useful? Like, why don't I just ask the question to the LLM? Well, check this out. Math or fact is a multiple choice question. That's easy. RAG is easy when you put the results. Doing a calculation is easy when you use the calculator app. And answering a question is easy when you got all the information from these ones. So every step here uses the rearview mirror. Nothing uses very much the headlights. And that's what you should do when you make agents. I'm gonna finish with a last question. When I started seeing agents, I noticed something which I didn't like. When I took my first programming course, it was object-oriented programming, which felt very much like agents, because it was like you have an object that does these functions, passes it here, passes it here, passes it here, the number passes here, and then you get an answer. And I thought, okay, is this really a way to charge more by calling it a fancier term? Because a lot of times AI does that. Is it just really object-oriented programming? And I thought that for a while, until finally I asked enough people and I worked on these things enough until I finally came to the realization that it is more. Because some things could go wrong. Let's say I have this question. I have 10 apples and I ate 2. How many do I have left? And I get the equation. And instead of 10 minus 4 in numbers, it replies 10 minus 4 in letters. Language models could do that. And that gives me an error with the calculator API. So the agent should be able to go back and talk to this one and say, hey, rewrite only using numbers, and then fix it. So this is called the agentic loop. That kind of stuff is what agents do that object-oriented programming could do if I tell it to. But the idea is that it can get out with results, with problems that I may have not coded it to solve. So I like to look at this progression. This is the last thing we'll see. And I have this should be static. I don't know why it's in Spanish. Sorry. It's static and dynamic. Okay. Automatization and autonomy. Here I have object-oriented programming, where I just give it the whole instructions and the program just follows my instructions. And if it runs into an error that I told it, it knows what to do. But if it runs into an error that I didn't plan and has no instructions, it crashes completely. On the other end of the spectrum, I have humans in a team. Humans in a team will follow instructions, but if there's a fire, somebody will bring out the bucket of water or something, right? They will know how to fix themselves. They would know how to hire a new person if they need something, or rearrange things in the team if somebody's getting too much work. They will be able to do a lot of things that are outside of the rules that I gave them, because they have they just have logic, right? They've been in the world. The idea of the agents, they're around here, right? They're more autonomous than object-oriented programming, and still not as autonomous as people in a team. And the goal is to move them as much as possible. The more they look like a team, the better. And they'll be able to sort of like fix problems that were not in the script. So that's how it differs from object-oriented programming. That's all the theory we'll learn today. Let's move to the labs. We have some time. They're not very long. So I have 3 labs, and I think, help me out, is Nabiha here, or maybe you can help me with did the labs get added to the resources for people to be able to open them? Or maybe Sanjay is here.
Yeah, just give us like 1 minute. I'm checking with Nabiha.
No problem.
Thank
Okay,
you.
sounds good. Thank you. In the meantime, you can open them. They're Google Colabs. They appear. You can use this to open them. I'll come back to this. And you need to get a Google AI Studio, an API key from Gemini. So I'll have these instructions here. Well, we need a minute before we can able to open them. In the meantime, before I leave, you should check out my YouTube channel, Serrano Academy. Let me put the link here. I have all these explanations. 1 second. In particular, I have some videos on this celestial mechanics, gravity stuff, and transformer mechanisms. I also have a book called Rocking Machine Learning if you want to check it out. So yeah, definitely check out Serrano Academy and follow me for more material. Okay, so for the labs, yes.
Luis, you were saying something. I totally missed it. Can you repeat?
Yeah. So if people want to open this, let me put the tiny URL link.
Yeah.
Lab 1, right? Bam. Try to open these 3 labs. They are the RAG, the calculator, and the matter of fact. Great question. Yes, I made them originally with StatQuest. So we put the word BAM. 2 reasons. Lab 1 rag is already taking in tiny URL. And so I threw in the word BAM, but it definitely comes from StatQuest. Yes. I work with him for workshops and stuff like that. Okay, so how are people doing with, are you able to open any of the 3 collabs? I can also open it myself here and just guide you. They're kind of simple. Basically the rag agent has 3 functions. So first, it's used in LangChain. So I import Wikipedia, LangChain, yabba yabba yabba. Then I do the Google environment key, which you can use it in the keys here. I have a Google key kind of in the secrets. Then I have one function that optimizes the prompt. So this one has a prompt that says, you're a query optimizer. Your goal is to rephrase user queries, yap. It gives it some instructions and some examples with a question and a reworded question, right? And then it basically, and this is for LangChain. It creates the sort of the pipes. It creates sort of the sequence of agents. And then I have optimized queries. So when I say, for example, gee, I'm wondering why did they make those pyramids that are in like Egypt or something, and it goes Egyptian pyramids, right? Then I have a function for searching in Wikipedia, which is basically called the API. And it returns a bunch of text, maybe more than what I need. And then formulating an answer simply puts them together, right? So I just say, use the original query, the optimized query, and the Wikipedia text to answer the question on a bunch of test cases. So this is just basically classic RAG. How are you doing with the opening the lab? Is anybody having a hard time opening the labs? The collabs? All good, fantastic. Then the calculator API is very similar, except it has a function that takes the text and turns it into the number, right? The equation in a pure equation mode, because I'm going to plug that string into a calculator. It can't have a word on it, right? So this part you have to be really, really strict that you have to provide only the equation itself. And I give it an example. What is 5 plus 3? It just goes 5 plus 3 in numbers. The next one performs the mathematical operation. So it just goes calculate equation. That's just API calling. There's no AI there. I'm calling the API of the calculator somewhere here. And then finally generate answer in a sentence. So I need the answer to be a sentence. So I use everything I got so far, the question, the reworded formula, and the answer for it to answer correctly. And then finally, the math or fact. Oh, perfect. Thank you for the links, Sanjay. Put your hand up immediately or talk on the microphone if you, yeah?
I got kicked out and somehow Zoom never let me in. So I think we have this in the learning portal too. Maybe last notebook we can show in our learning portal.
Thank you so much. Yeah. Do
Sorry,
you want me to
about
open them
that.
in the learn? Oh no, please. Oh yikes! I don't know. This. Oh, I have to log in. 1 second. I'll wait till any accounts. Oh, this is nice. Thank you for loading them. By the way, this is lab and also questions. By the way, if there's any questions about the lecture, you can also either say them or put up your hand or tell them in the chat. I'm opening math or fact. You can also share feedback for Luis' workshop. It's like an Uber feedback. Okay, so here's math or fact, right? I have the classifier agent, I have the math agent, and I have the fact agent. By the way, there's a small thing, and it's like, I don't know how many credits Google gives. Normally, by the time I get to the last question here, I start running out of credits. So don't run them too many times to try until you go through the third lab. Yeah, so this one, I pretty much copy pasted the functions for the others for calculator agent. And here I have a classified query. So I say classify query into math, fact, or none. And then, so for example, if I say a math question, it just replies math. If I say a fact question, it replies fact. And if I ask something else, it replies none. And then return response, basically, this uses the classification from the previous one, and it helps it. It says, answer this question, it's math. So it pipes it to the calculator agent. And if it's fact, it pipes it to the fact agent. And if it's something else, it just says, I don't know. I'm only trained to do math or fact. So yeah, I mean, the labs is pretty much, take your time looking at it. Feel free to ask any questions. But it's basically the first agent. The first agent's always RAG. And I'm here, we have 15 minutes. So I'm basically here for questions or anything. And I see the first question. See, it says, could you talk about the math behind viewing the space as undergoing a nonlinear transformation versus the function undergoing nonlinear transformation? And you're like, oh, that's a good question. Wait, let me wrap my head around it. Could you open your mic and maybe tell me a little more? Oh, I see. Like the ReLU? Yeah. Oh, the decision boundary. Yes. Let me go back here. Where were we? Feed forward. This, right? So here's how I imagine it. Obviously, this is not two-dimensional, right? This is actually, here's an example. Here's how to turn something linear into something non-linear. Let's say that I have a sheet, maybe not of paper, but like a sheet of like a sheet, right? And I want to draw a circle, but I only have linear cuts. Okay, so how can I draw a circle using linear cuts? I can't really go, everything I have to do is either a line or a plane. So picture this, I take the sheet and I lift, and now I have a bump. And now I cut with a plane. What I did was a circle, right? But I never drew a circle. I just used a linear cut. So that's what happens here. If this space has, let's say, 1,000 dimensions, maybe this one has 1,000,000 dimensions. All right, this is huge, right? But the fact is, if I bend it and bend it and bend it and bend it, and I draw a linear cut in the original, when I embed it, it could be a really complicated cut, right? That's kind of how I picture neural networks. This is not necessarily a function, but it's just a plane in a much higher dimensional space that when you undo, it wasn't a plane. In the same way that I had a two-dimensional sheet, I made it three-dimensional by cutting a bump, by raising a bump. I cut with a plane, and when I go back, I have something that's nonlinear. It's a circle. So I can create nonlinear stuff by adding dimensions and doing linear cuts. You see what I mean? So I don't think of a function yet. The function is the one that sends this to this. That's the function, right? Takes every point here, goes to some point here. This dog goes to this thing. This apple goes here. So every point in this space goes to a point in the space. That's the function. And if that function was only linear, then this would be a parallelogram. But the fact that I'm breaking it with my ReLU and then applying another parallelogram and breaking, means I can get as crazy as I want here. Right? I don't know if I answered your question. Is that more clear? Yes. And normally neural networks add dimensionality. That's why here, for example, you start with 4 dimensions, then you went to 6. You live in a bigger world, right? You're like, everything's so big, and then you're again in 6, and then you go down, crash to 2, right? So this is what we did, right? We took the thing, some dimensions, brought it up to lots and lots, and you're a little ant, and then boom, crunch it down to 2. And somewhere in the process, you manage to put all the cats on one side. Right? That's sort of that. Yeah, okay, thank you. Great question. We have 10 minutes left. Yeah, I mean, I'm happy to answer any questions, or if anybody with the labs are more play on your own, right? But if you want to go through them right now or on your own time, let me just fix this thing here. If you want to go over them right now on your own time, basically just an implementation of RAG and an implementation of the calculator agent. Thank you so much, Kumar. Thanks for your feedback. Kieran says positional encoding. Sure, I can re-explain positional encoding. Yeah. By the way, I have a video on position encoding, and you can take a look. Thank you for everybody saying. Thank you, Ricardo. Thanks for saying you enjoyed the session. I really enjoyed it too. You all answered my questions very well. Well, let's take 5 minutes and re-explain positional encoding if it was not clear. And by the way, any other questions, feel free to add them in the chat, and I think we'll have time to go through everything. So here's positional encoding, okay, Kieran. When I have sentences that are in the wrong order, like these two, the embedding doesn't know because it puts them in the same place, right? The embedding sees 4 things, and this embedding sees the same 4 things, but the order is not there. So I'm gonna encode the order by moving every word in a different position. So the first word gets moved to the right, the next one up, and so on. And if I do this, then now things go to different places, and now I have 2 different things. So I want to break these things into 2 different things, right? And oh, thank you for adding the Sanjay. Thanks for adding the positional encoding thing. So I need a sequence, right? So here's what I do. I move the first word in some angle, the next one in an angle, and so on. But eventually that's not good because I get back to where I started. And I don't want to have the 11th word similar to the first word. So I can't really do something periodic like this. But periodic is nice because the model has to learn it, right? The model has to be able to reverse engineering. And so what I do is I take the first 2 entries in the embedding, and I do that rotation, right? For the first word, for the second, for the third. And for the next 2, I do a smaller angle. Like I spin the wheel slower. And for the next one, I spin the wheel much slower. And so on. And basically that's positional encoding, right? Let me know if it's not clear. Oh, Robert has a question. You have longer sentences, the impact of positional encoding decreases. Yeah, that's a great question, Robert. If you have more than longer sentences, I would say, yeah. So if I have a really long, like for example here, if my sentence is 11 words long, the 11th word gets moved just like the first word, so that's not good. Now, here's the question. So if my embedding has 1,000 words, if my embedding has, let's say, 1,000 entries, the 999 and the 1,000, the last 2 entries get moved pretty much to the right because this dial is really slow. So for me to be able to go back and go the full circle on the last two, my sentence has to be stupidly long. And context windows are smaller than that. So you see, positional encoding is periodic. At some point, the sentence is long enough that the 1 trillionth word gets moved in the same way as the first word. But that 1 trillion is bigger than the actual context window of ChatGPT. So it's not going to be a problem. Like it's periodic, but it's so slow periodic that we're not going to be able to see it because it just leaves the memory of ChatGPT, right? Yes, absolutely. As context windows increase, definitely something to watch. But I think this 10,000 is really big. The 10,000 power is, see, when this number is big, 10,000 to this number is huge, and this basically becomes 0, right? So this is cosine of 0 and sine of 0, which is pretty much this vector here, 1, 0, right? So absolutely, if context window of ChatGPT gets huge, then we should rethink positional encoding. But it could just be rethinking by making this number bigger, right? I don't know if we have to have a different algorithm other than just changing this number. I'm just guessing. See, it's a Gemini has 1 million token context window. Okay. I feel like 1 million is still not enough to actually turn this thing. Maybe I have to do the math, but yeah, definitely. Definitely you don't want the thing to be periodic. So it's something to like balance out. And then Sanjay says geometric one feels more embodied than algebraic. Oh, you mean the wheel spinning versus this cosine of position divided by 10,000 over to the 2i divided by d?
Like you usually when you positional encoding, we only see the equations, right? But
yeah, that's like
we're showing the geometric.
Getting punched in the face. Thank you. Yeah, I feel like when I see formulas, I get lost, so I have to have some wheel spinning somewhere. Thanks. All right, how do we feel? We have 3 minutes. Any other questions? These are great questions, by the way. Well, thank you so much. I really enjoyed our chat. Any last thoughts? Don't forget to check out the YouTube channel. And yes, this recording will be shared, right? Well, thank you. Thank you so much for the great questions and for answering my questions. Stick around in case more questions come up, but pretty much wrapped up. Thank you. Thank you. Cool. Well, thank you very much. That was such nice comments. Thanks again. Thanks, Nami. All right. Bye, everybody. Have a great rest of the day. Enjoy the rest of the conference. I'll leave it in Navija's hands.
Perfect. Thank you so much, Luis, for such a wonderful session. And thank you, everyone, for joining. I saw that there were questions about the workshop recording. So we will be sending that to you early next week with the resources as well. And yeah, that's it. Thanks, everybody, for joining. And thank you so much, Luis, for such a composed workshop. It was really good.
Thank you. Thank you so much. Thanks for hosting, and thanks everybody for being here. I appreciate your time. Thank you.
Thank you. Bye-bye. Take care, everyone.
Bye-bye.